Hello, friend. Welcome back to another journey through the cosmos, where we explore the quiet wonders that dance above us every night. Have you ever laid on your back on a summer evening, gazing up at the stars, and noticed them flickering like tiny candles in an invisible wind? That gentle shimmer, that delicate dance of light, ancient observers called it the trembling of the heavens. But here's what's fascinating. For thousands of years, the greatest minds in human history got the explanation completely wrong. And the truth, it's far more beautiful than anyone imagined. If you're finding peace in these cosmic stories, I'd be grateful if you'd tap that like button and subscribe. It helps others discover these quiet moments of wonder, and it means the world to me. Thank you for being here. Now, let's travel back to a time when the night sky wasn't dimmed by city lights, when every human being grew up intimately familiar with the stars. Picture Babylon, around 1800 BCE. Priests climbed the ziggurats at dusk, clay tablets in hand, ready to record the movements of the heavens. These weren't just casual stargazers. They were meticulous observers who tracked celestial patterns for generations. And they noticed something peculiar. While most stars twinkled and danced, a handful remained steady, like calm lights floating through a sea of trembling flames. They called these steady lights wanderers, planets, though they didn't yet understand what made them different. The Babylonian astronomers documented this distinction with remarkable precision. On tablets that have survived nearly 4,000 years, we can read their observations. The star Dilbat, what we call Venus, shone with unwavering light. So did the red star they called Salbatanu, Mars. But the countless other stars, those fixed points that never moved relative to each other, all seemed to flicker and shimmer. Why would the wanderers behave differently? The tablets ask this question implicitly, but they offer no answer. It was simply one more mystery in a sky full of them. Fast forward to ancient Greece, around 350 BCE. Aristotle, one of history's most influential thinkers, turned his attention to this celestial trembling. His explanation seemed logical for his time. He proposed that stars twinkled because of the vast distance between Earth and the heavens, combined with the weakness of our vision, trying to perceive such remote lights. The stars weren't actually moving or changing, he argued. It was simply the limitation of human sight, like trying to see a distant torch through tears. Our eyes, straining across impossible distances, created the illusion of movement. It was a reasonable guess, and it was completely wrong. But here's what makes this fascinating. Aristotle actually got part of the puzzle right by accident. He noted that planets don't twinkle. He explained this by claiming planets were closer to Earth, making them easier for our eyes to perceive steadily. The reasoning was flawed, but the observation was accurate. Ancient Greek astronomers, like their Babylonian predecessors, clearly distinguished between the twinkling stars and the steady planets. This distinction would become crucial, not for understanding twinkling, but for understanding the very structure of our solar system. It was one of the clues that eventually helped humanity realize planets were fundamentally different from stars. Aristotle's explanation dominated Western thought for nearly 2,000 years. When you're Aristotle, people tend to believe you for a very long time. Meanwhile, halfway across the world, Chinese astronomers were making their own detailed observations. The Tianguan Shu, the Book of Celestial Officials compiled during the Han Dynasty around 100 BCE, contains extensive records of stellar observations. Chinese astronomers noticed that stars near the horizon twinkled more intensely than stars directly overhead. This was a crucial observation, one that pointed toward the real explanation. But the connection wasn't made, not yet. Then, in the 11th century, something remarkable happened. An Arab mathematician and physicist named Ibn al-Haytham, known in the West as Al-Hazen, was conducting experiments with light. He wasn't studying stars at all. He was investigating how vision works, using lenses and water-filled spheres to understand how light bends when it passes from air into glass or water. He discovered the principle of refraction, the bending of light as it moves between materials of different densities. In his masterwork, The Book of Optics, Alhazen described how atmospheric thickness affects the appearance of celestial objects. He explained that light from stars travels through increasingly dense air as it approaches Earth's surface, causing the light to bend. And here, buried in a 7-volume treatise on optics and vision, was the first real clue to explaining stellar twinkling. The atmosphere itself was bending starlight. But Alhazen didn't quite complete the puzzle. He understood refraction through a stable atmosphere, light bending as it passed through layers of different density. What he didn't realize was that the atmosphere isn't stable. It's in constant motion, constantly turbulent. That turbulence is the key. Still, his work represented a monumental leap forward. The answer wasn't in the stars or in our eyes. It was in the air itself. Alhazen's works were translated into Latin in the late 12th century, profoundly influencing European scholars. Yet somehow, the connection to stellar twinkling wasn't immediately grasped. Medieval European astronomers continued to rely on Aristotelian explanations. It's a reminder that scientific progress isn't a straight line. Sometimes the pieces of a puzzle sit separately for centuries before someone realizes they fit together. The practical consequences of stellar twinkling weren't abstract or academic. They were matters of life and death. Medieval and Renaissance sailors navigated by the stars, using instruments like astrolabes and cross staffs to measure the angle of celestial objects above the horizon. But twinkling stars don't stay in one position. They shimmer and shift, making precise measurements difficult, sometimes impossible. Ship logs from the 15th and 16th centuries describe the frustration. Portuguese sailors exploring the African coast wrote of stars that danced and would not hold still when viewed through their instruments. Navigational errors of even a single degree could put a ship dozens of miles off course, potentially the difference between finding safe harbor and wrecking on unseen rocks. Sailors learned through hard experience to take multiple readings and average them, to make measurements when stars were highest in the sky, where the twinkling was less severe. But they didn't know why stars high overhead were steadier. They simply knew it was true. Some sailors noticed another curious pattern. Stars twinkled more on humid nights and less on cold, dry nights. Again, the observation was correct, but the explanation remained a mystery. Humidity affects atmospheric turbulence, but that wouldn't be understood for centuries. By the Renaissance, European astronomers were rediscovering and building upon Alhazen's work on optics. Figures like Johannes Kepler, who lived from 1571 to 1630, understood that Earth's atmosphere bent light from celestial objects. Kepler correctly explained why the sun appears to rise slightly earlier than it geometrically should. Atmospheric refraction lifts the sun's image before the sun itself actually crests the horizon. He also understood that this refraction affected star positions, but Kepler still didn't explain twinkling. The distinction is subtle but crucial. Refraction through a stable atmosphere explains why stars appear in slightly different positions than they actually are. But twinkling, the rapid shimmer, the fluctuation in brightness and color, requires something more. It requires turbulence, chaos, constant motion in the air. That understanding wouldn't solidify until the development of modern physics in the 19th and 20th centuries. Let me share one more story from this era, a mistake that illustrates how confusing stellar twinkling was, even for brilliant observers. John Flamsteed, the first astronomer royal of England, established the Royal Observatory at Greenwich in 1676. His task was to create precise star catalogues for navigation. Flamsteed was meticulous, one of the most careful observers of his generation. But in his early catalogues, he noted certain stars as variable, changing in brightness from night to night, sometimes even within a single night. Some of these stars were genuine variable stars, their light actually fluctuating due to stellar processes. But others, they weren't variable at all. Flamsteed was observing the effects of extreme atmospheric scintillation on particularly bright stars near the horizon. The stars weren't changing. The air between the telescope and the stars was changing. It took decades to sort out which stars were truly variable and which appeared variable only because of atmospheric effects. This confusion persisted well into the 1700s. Imagine being an astronomer trying to map the unchanging heavens and finding that stars near the horizon seem to pulse and vary, while the same stars observed from different locations or different seasons behave differently. The sky itself seemed inconsistent, almost as if it were playing tricks. What these ancient and early modern observers were circling around, what they sensed but couldn't quite articulate, was this: Earth sits at the bottom of an ocean of air, not a calm, still ocean, but a churning, turbulent one, with currents and eddies invisible to the eye but constantly in motion. Every photon of starlight, light that has traveled for years, decades, or centuries across empty space, must pass through this final 100 miles of turbulent air before reaching our eyes. And in those final moments of its journey, the light gets jostled, bent, split, and scattered in constantly changing ways. The stars themselves are steady. They shine with unwavering light across the vastness of space. But by the time that light reaches us, it has been transformed by its passage through Earth's restless atmosphere. The trembling isn't in the heavens, it's in the air. Think about that for a moment. Ancient humans lay under the same stars we see tonight. They saw the same gentle shimmer, the same delicate dance of light. They wove it into their poetry and mythology. They saw it as evidence of the divine spark in celestial objects, as proof that the heavens were alive. And in a sense, they were right. Not because stars actually twinkle, but because the phenomenon reveals something profound about our world. It reveals that we live beneath a dynamic, ever-changing veil, that every glimpse we have of the cosmos is filtered through our planet's breathing atmosphere. For thousands of years, humanity looked up at twinkling stars and wondered why. The answer was always there, surrounding us, invisible but omnipresent. The air itself, the atmosphere we breathe, was the cause of this ancient mystery. But knowing the cause is only the beginning of understanding. What exactly is happening in that turbulent ocean of air? How does it transform starlight into that characteristic shimmer? To answer that, we need to understand Earth's atmosphere not as empty space, but as a complex layered structure with its own physics, its own rules, its own secret dance. We live at the bottom of an ocean we can't see, an ocean that's constantly in motion, constantly churning. Right now, as you listen to this, you're surrounded by invisible currents and eddies, by pockets of air at different temperatures and densities, all swirling and mixing in patterns so complex that even our most powerful computers can't predict them perfectly. And every single photon of starlight that reaches your eyes must swim through this turbulent sea. This ocean has layers, just like the ocean of water. And understanding these layers, their structure, their movement, their invisible architecture, is the key to understanding why stars twinkle. So, let's dive in, quite literally, into the atmosphere above us. If you're enjoying this journey through the cosmos and the science that explains its wonders, a like would mean so much, and subscribing ensures you won't miss future explorations. Your support keeps these stories alive. Thank you. Let's start with something tangible, something you can actually feel. Step outside on a summer day when the air is hot and still. Hold your hand 6 inches above a sun-baked road or parking lot, and you'll feel heat rising in waves. Now, look at the air just above that hot surface. You might notice something strange. The air seems to shimmer, to waver, like you're looking through moving water. Distant objects appear distorted, rippling. This is atmospheric turbulence made visible by extreme temperature differences. That shimmering effect you see above hot pavement, that's essentially what's happening to starlight, except it's happening throughout the entire column of air between you and space, a column that stretches upward for 60 miles or more. Earth's atmosphere isn't uniform. It's structured in distinct layers, each with its own characteristics, its own behavior. The layer we live in, the one we breathe, is called the troposphere. It extends from ground level up to about 5 to 9 miles high, depending on your latitude. The troposphere is where all weather happens, all clouds, all storms, all rain and snow. It's also the most turbulent layer, the one that causes the most trouble for starlight trying to reach us. Why is the troposphere so turbulent? Because it's heated from below. The sun warms Earth's surface, and that warm surface heats the air touching it. Warm air is less dense than cool air, so it rises. As it rises, it cools and eventually sinks again. This creates circulation patterns called convection cells. You can think of them as invisible rotating wheels of air, some small, some enormous, all turning at different speeds and interacting with each other. But it's not just simple up and down motion. The Earth is rotating, creating the Coriolis effect. There are jet streams, rivers of fast-moving air at high altitude. There are mountain ranges forcing air upward, coastlines where sea breezes meet land air, urban areas creating heat islands. All of these factors create turbulence, chaotic, constantly changing motion in the air. Now, here's the crucial part. Air density changes with temperature. Warm air is less dense than cold air. And when light travels through materials of different densities, it bends. That bending is refraction, the principle that Alhazen discovered in the 11th century. But Alhazen was thinking about light passing through stable layers of atmosphere, like light moving from air into water, a one-time bend. Stellar twinkling happens because the atmosphere isn't stable. Those pockets of warm and cool air, those turbulent eddies and currents, are constantly moving and mixing. So, starlight doesn't encounter one stable layer. It encounters thousands of constantly changing pockets of air, each with slightly different density, each bending the light slightly differently, and these pockets are moving and changing from millisecond to millisecond. Imagine trying to shine a laser pointer through a swimming pool while someone splashes around in it. Sometimes the water moves and focuses the beam, making it brighter. Sometimes the water scatters it, making it dimmer. Sometimes the water bends it one direction, sometimes another. That's what's happening to starlight in the atmosphere, except it's happening incredibly fast. The changes occur in fractions of a second. Astronomers have a technical term for how turbulent the atmosphere is at any given time. They call it seeing. Good seeing means the atmosphere is relatively calm, producing steady, sharp images of stars. Poor seeing means heavy turbulence, causing stars to twinkle wildly and telescope images to blur. Professional observatories measure seeing conditions constantly, and these measurements can be surprisingly precise. One common measure is called the Fried parameter, named after physicist David Fried, who formalized it in 1965. The Fried parameter describes the diameter of atmosphere across which the phase of incoming starlight remains relatively coherent. In simpler terms, it tells you how big a patch of turbulence-free air you're looking through. On a good night at a good observatory, the fried parameter might be 6 to 8 inches. On a poor night, it might be just 2 inches. For context, most serious telescopes have mirrors measured in feet or even meters, meaning the atmosphere is breaking up the light across the entire mirror into dozens or hundreds of independently twinkling patches. Think about what this means. You build a telescope with a mirror 8 feet across, capable of gathering tremendous amounts of light and resolving incredibly fine detail. But on a typical night, the atmosphere effectively breaks that mirror into perhaps 50 or 100 separate small patches, each seeing slightly different turbulent air. The full potential of your telescope is stolen by the atmosphere. This limitation drove astronomers to build observatories in specific locations, and eventually to put telescopes in space. But we'll return to those stories later. Weather patterns dramatically affect seeing conditions. When a high-pressure system sits over an observatory, bringing stable, calm air, the seeing improves. When low-pressure systems move through, bringing storms and fronts where air masses of different temperatures collide, seeing deteriorates. Astronomers plan their observing runs around weather forecasts, hoping for stable conditions. Humidity matters too, though not in the way you might expect. Water vapor itself is actually less dense than dry air, a fact that surprises many people. But humid air tends to occur in conditions that also produce turbulence. Humid air is often associated with temperature variations, with mixing air masses, with instability. Professional observatories often track not just temperature and humidity, but also the temperature gradient, how quickly temperature changes with altitude. A steep temperature gradient usually means poor seeing. Here's something fascinating that took astronomers decades to fully appreciate. The height of turbulence matters as much as its intensity. Turbulence right above the telescope, in the first few hundred feet of atmosphere, causes one type of distortion. Turbulence at high altitude, where the jet stream flows 6 to 7 miles up, causes different distortions. Modern adaptive optics systems, which we'll explore in detail later, have to account for turbulence at multiple altitudes simultaneously. Now, let's talk about a phenomenon you've probably observed without realizing its significance. Stars twinkle much more when they're near the horizon than when they're directly overhead. Why? The answer is geometry. When you look at a star directly overhead, starlight passes through the minimum thickness of atmosphere, straight down through maybe 60 miles of air. But when you look at a star near the horizon, the starlight comes in at a steep angle, passing through vastly more atmosphere, potentially hundreds of miles of air, all of it in the densest, most turbulent lower layers. To make this concrete, a star at the horizon passes through approximately 38 times more atmosphere than a star directly overhead. 38 times more turbulence, 38 times more opportunities for the light to be bent, scattered, and distorted. This is why Sirius, the brightest star in our night sky, puts on such a spectacular show when it's low on the horizon. Sirius is bright to begin with, so it's sending lots of light toward Earth. But when it's near the horizon, that light must traverse an enormous column of turbulent air. The result is dramatic twinkling, often with rapid color changes, flashes of blue, white, red, even green, all in quick succession. Ancient sailors sometimes reported Sirius as appearing to rage or boil when low on the horizon. They weren't exaggerating. They were accurately describing intense scintillation. Medieval and Renaissance astronomers knew this pattern well. They developed a practical rule: never try to make precise measurements of stars within about 15 degrees of the horizon. The turbulence-induced distortions were simply too severe. Even today, with modern instruments and adaptive optics, observations near the horizon remain problematic. Mountains became crucial for astronomy precisely because they lifted telescopes above the densest, most turbulent part of the atmosphere. The Mauna Kea Observatory in Hawaii sits at 13,696 feet above sea level. At that elevation, the observatory is above roughly 40% of Earth's atmosphere by mass. More importantly, it's above most of the water vapor and weather-related turbulence. Compare Mauna Kea to the historic Royal Observatory at Greenwich, England, which sits at just 155 feet above sea level. Greenwich's telescopes peer through the entire thickness of Earth's atmosphere, including all the turbulent lower layers. This difference is dramatic. On an average night, Mauna Kea experiences seeing conditions 3 to 4 times better than Greenwich. Stars appear sharper, steadier, clearer. But even Mauna Kea isn't perfect. Even at nearly 14,000 feet, there's still atmosphere above, still turbulence. Astronomers dreamed of going higher, and eventually they did, by putting telescopes in space or on high-altitude aircraft. But before we get there, we need to address a common misconception about what causes turbulence. Many people assume that heat rising from Earth's surface is the primary cause of stellar twinkling, and heat does play a role, but not in the way most people think. It's not the rising motion of air that causes twinkling. It's the temperature differences and resulting density variations. Air can be moving rapidly without causing much twinkling as long as the temperature is uniform. Conversely, air can be relatively still but cause severe twinkling if there are sharp temperature gradients creating pockets of different density. The turbulence that matters for stellar scintillation is specifically turbulence that creates optical variations, changes in the refractive index of air. This distinction is important because it helps explain some otherwise puzzling observations. For instance, nights with strong, steady winds often have excellent seeing. The wind is mixing the air, creating uniform temperature and density. Conversely, calm nights with no wind sometimes have terrible seeing, because temperature inversions and stratification can create sharp boundaries between air masses of different temperatures. Professional astronomers have learned to read atmospheric conditions with remarkable skill. They can look at how stars appear near the horizon and predict how well the telescope will perform that night. They can feel the wind and temperature and make educated guesses about seeing conditions at different altitudes. It's part science, part accumulated experience, the kind of knowledge that comes from spending hundreds of nights under the stars, learning to interpret the atmosphere's moods. Let me share a specific example that illustrates how complex atmospheric turbulence can be. The Gemini North Telescope in Hawaii routinely measures atmospheric conditions at multiple altitudes simultaneously. On one particular night in January 2009, instruments showed excellent seeing conditions for the lower atmosphere. The first half-mile above the observatory was calm and stable, but at altitude, where the jet stream flows, there was significant turbulence. The result was an unusual pattern. Bright stars appeared relatively steady, but faint stars, which require longer exposure times and therefore average over more turbulent variations, showed significant distortion. This illustrates an important point. The atmosphere isn't a single uniform thing. It's a three-dimensional structure with turbulence at different layers, different intensities, different time scales. Some turbulent cells are tiny, just inches across. Others are enormous, stretching for miles. Some change in milliseconds, others evolve over minutes. Starlight must navigate all of it. There's even seasonal variation in seeing conditions. Winter often brings better seeing than summer because cooler temperatures mean less thermal turbulence near the ground. But winter also brings storms and fronts, which can cause their own problems. Spring and fall, with more stable weather patterns, often provide the best observing conditions. Experienced amateur astronomers learn these patterns for their local area, planning their most ambitious observations for seasons when the atmosphere is likely to cooperate. The jet stream deserves special mention. This narrow band of high-speed wind, typically flowing at 25,000 to 35,000 feet altitude, can reach speeds of 200 miles per hour or more. When the jet stream passes overhead of an observatory, it often creates significant turbulence. But here's what's interesting. The turbulence isn't from the fast-moving air itself. It's from the boundaries where jet stream air meets slower-moving air above and below it. Those boundaries create shear, and shear creates turbulence. Meteorologists can predict jet stream positions days in advance. Modern observatories incorporate jet stream forecasts into their scheduling, trying to plan critical observations for nights when the jet stream will be far away. This is the kind of detailed atmospheric knowledge that separates good observing conditions from exceptional ones. One more factor that affects stellar twinkling: local geography. Observatories near coastlines often experience good seeing when wind flows from the ocean, bringing air that has traveled over uniform temperature water, resulting in stable, homogeneous air masses. Observatories near cities suffer from urban heat islands. Cities are warmer than surrounding countryside, creating thermal turbulence. Mountains create their own wind patterns as air flows up slopes during the day and down at night. All of these local effects overlay the broader atmospheric patterns. The Paranal Observatory in Chile, home to the Very Large Telescope, was chosen in part because of its exceptional seeing conditions. Paranal sits in the Atacama Desert at 8,145 feet elevation, far from cities, in one of the driest places on Earth. The combination of high altitude, dry air, distance from urban heat, and stable atmospheric conditions makes Paranal one of the best locations on the planet for optical astronomy. On exceptional nights, the seeing there can be better than half an arc second. That means stars appear as tiny, sharp points, with minimal twinkling even through powerful telescopes. Half an arc second is incredibly small. It's equivalent to resolving 2 headlights on a car from 300 miles away. The fact that Earth's turbulent atmosphere allows such sharp views at all, even from the best locations, is somewhat remarkable. It also illustrates just how much better seeing could be without atmosphere, and why space telescopes revolutionized astronomy. But that's a story we'll come to later. For now, consider this. We've traced the mechanism. We understand that stellar twinkling comes from turbulent pockets of air at varying temperatures, creating constantly changing density variations, which bend light in constantly changing ways. We've seen how this turbulence varies with altitude, with weather, with season, with geography. We've learned how astronomers measure and predict atmospheric conditions, but we haven't yet explored the physics in detail. How exactly does light bend when moving through air of different densities? What are the mathematical rules governing this bending? And why does this bending sometimes make stars brighter, sometimes dimmer, sometimes appear to jump from position to position? To answer those questions, we need to go deeper into the physics of light itself, into the elegant mathematics of refraction, the quantum mechanics of photons passing through matter, the wave properties of light interfering with itself. Light travels at 186,082 miles per second in empty space. Nothing in the universe moves faster. But here's something that surprises most people. Light slows down when it enters matter. Air, water, glass. Any material makes light travel slightly slower. And when light slows down at an angle, something elegant and inevitable happens. It bends. This bending, this change in direction we call refraction, is what transforms steady starlight into that characteristic shimmer we see from Earth. Understanding refraction means understanding twinkling. So let's explore the physics that turns straight paths into curves, that transforms the journey of light through our atmosphere into something far more complex than you might imagine. If this exploration of light and physics resonates with you, I'd be grateful for a like. It helps others discover these stories. And if you'd like to continue this journey through the cosmos, subscribing means you'll never miss what comes next. Thank you for being here. Let's start with an experiment you can do right now, or at least visualize clearly. Fill a glass with water, not quite to the top, leave a little space. Now, place a pencil or pen in the water at an angle, so part of it is submerged and part of it sticks up into the air. Look at it from the side. The pencil appears to bend at the water's surface. The underwater portion seems to be at a different angle than the part in air. If you didn't know better, you'd swear the pencil was actually broken at the waterline. But of course, it's not broken. The pencil is perfectly straight. What's bending is the light traveling from the underwater portion of the pencil to your eye. This simple observation puzzled natural philosophers for centuries before it was properly explained. Ancient Greek scholars noticed it. Roman scholars wrote about it. But the mathematical explanation, the precise rules governing how much light bends, wasn't worked out until the early 17th century. In 1621, a Dutch mathematician named Willebrord Snellius discovered what we now call Snell's law. The story of this discovery is interesting in itself. Snellius never published his finding. It was discovered in his manuscripts after his death. The same law was independently discovered by René Descartes in 1637, who did publish it. For a while, it was called Descartes' law of refraction. History eventually credited Snellius, but it's a reminder that scientific discoveries often have complex, tangled origins. Snell's law states that when light passes from one material into another, the angle of bending depends on a property called the refractive index. Every material has a refractive index, a number that describes how much that material slows down light compared to empty space. The refractive index of vacuum is exactly 1.0 by definition. The refractive index of air at sea level is about 1,293, very close to 1.0, but not quite. The refractive index of water is about 1.333. The refractive index of typical glass is around 1.5. These might seem like small numbers, but they have profound effects. When light traveling through air hits water at an angle, it slows from about 186,282 miles per second to about 140,000 miles per second. This sudden change in speed causes the light's direction to change. It bends toward the perpendicular to the surface. Here's a helpful way to visualize why this happens. Imagine a marching band on a parade ground moving forward in a straight line. Now, suppose the left side of the band reaches muddy ground first, where marching is slower. The left side slows down, while the right side is still moving at full speed. What happens? The line of marchers pivots. It bends toward the left, toward the side that slowed down first. Light does the same thing. When one part of a light wave enters a slower medium before another part, the wave pivots, changing direction. The mathematical formula is elegant. N1 sin, Th1 shas N2 sin, Th2, where N1 and N2 are the refractive indices of the two materials, and Fe1 and Th2 are the angles of the light path measured from perpendicular to the surface. Don't worry about memorizing it. What matters is the principle. The greater the difference in refractive index, the greater the bending. And the more extreme the angle at which light hits the boundary between materials, the more dramatic the bending. Now, here's where it gets relevant to stellar twinkling. Air doesn't have just one refractive index. The refractive index of air depends on its temperature, pressure, and composition. Warm air is less dense than cool air, so it has a slightly lower refractive index. Humid air has a different refractive index than dry air. Air at high altitude where pressure is lower, has a different refractive index than air at sea level. These differences are tiny. We're talking about changes in the 4th decimal place, but they're enough. When starlight passes through a pocket of warm air surrounded by cooler air, it bends. When it passes from dry air into more humid air, it bends again. The atmosphere isn't uniform. It's a 3-dimensional patchwork of air with slightly different refractive indices. And all these patches are constantly moving, constantly mixing, constantly changing. Every time starlight crosses a boundary between air masses of different temperature or density, Snell's law applies. The light bends according to the change in refractive index. And because these boundaries are constantly shifting, the amount and direction of bending changes from moment to moment. Let's make this more concrete with actual numbers. The refractive index of air at sea level and 15 degrees Celsius is approximately 1,293. Increase the temperature to 30 degrees Celsius, and the refractive index drops to about 1,279. That's a difference of just 0.0014, an incredibly small number. But across 60 miles of atmosphere, with light potentially crossing thousands of boundaries between air masses of different temperatures, these tiny differences accumulate. A single passage through one turbulent eddy, a pocket of air just a few feet across with a temperature 5 degrees different from surrounding air, will bend starlight by a tiny amount, perhaps a few thousandths of an arcsecond. But starlight doesn't pass through just one eddy. It passes through dozens, hundreds, even thousands of turbulent cells as it descends through the atmosphere. Each one bends the light a little. The bends don't all point in the same direction. Some bend the light left, some right, some up, some down. The cumulative effect is a rapidly changing dance, a shimmer, as the light's path constantly adjusts to the changing atmosphere. Here's something that took physicists a while to fully understand. These refractive bends don't just change the position of the star's image, they also change the intensity, the brightness. How? Imagine starlight as a parallel beam, millions of photons traveling side by side, all in the same direction. Now that beam enters the turbulent atmosphere. Different parts of the beam pass through different turbulent cells. Some parts get bent slightly left, some slightly right. The beam spreads out. It gets defocused. When it reaches your eye or a telescope, it's spread over a larger area, so the brightness appears dimmer. But wait, there's another possibility. Sometimes the turbulence acts like a lens, focusing light instead of spreading it. A particular arrangement of air with the right temperature gradient can create a temporary moving lens effect. When this happens, light that would normally miss your eye gets bent toward it. Suddenly, more photons arrive than usual. The star appears brighter. These focusing and defocusing events happen randomly, rapidly, constantly. The result is that characteristic flickering. The star brightens, dims, brightens again, all in fractions of a second. It's not regular, it's chaotic because atmospheric turbulence is chaotic. But it's also not completely random. There are patterns, time scales, correlations that atmospheric physicists have learned to measure and predict. The typical time scale of stellar scintillation, the time between brightness fluctuations, is about 0.01 to 0.1 seconds. Why these particular time scales? Because that's how fast atmospheric turbulent cells typically move across your line of sight to a star. The wind carries these cells, and as different cells move into and out of the path between you and the star, the refraction pattern changes. Strong winds actually help in a way. They move turbulent cells through your line of sight more quickly, so the scintillation is faster, but also averages out more rapidly. With slow winds, turbulent cells can linger, causing sustained brightening or dimming. Astronomers taking long exposure photographs in slow wind conditions sometimes see star images that are elongated or distorted in particular directions, reflecting the sustained presence of refractive structures in the air. Now, let's talk about something truly fascinating: wavelength dependence. Light isn't just light. It's a spectrum of colors, from red to orange to yellow to green to blue to violet. Each color is a different wavelength. Red light has a wavelength of about 700 nanometers. Blue light is about 450 nanometers. Here's the key point. The refractive index of air depends on wavelength. This phenomenon is called dispersion. Blue light has a slightly higher refractive index in air than red light. This means blue light bends more than red light when passing through the atmosphere. For steady, uniform atmosphere, this just means that blue stars appear slightly displaced compared to where red stars appear. A tiny effect that astronomers can correct for. But in turbulent atmosphere, dispersion has a dramatic consequence. Different colors get bent different amounts by the same turbulent cell. When starlight passes through a turbulent eddy, the red component might get bent slightly left, while the blue component gets bent slightly right. They separate. The single white starlight gets split into colors. Milliseconds later, as the turbulence changes, the colors might converge again, or split in a different direction. The result is that stars appear to flash different colors as they twinkle. This is chromatic scintillation, and it's especially visible for bright stars near the horizon. Sirius, which we mentioned earlier, shows spectacular chromatic scintillation. Rapid flashes of blue, white, red, even hints of green. Ancient and medieval observers were mystified by these color changes. Some thought they were watching actual changes in the star itself. We now know it's entirely atmospheric, a consequence of dispersion combined with turbulence. The amount of dispersion, the separation between blue and red light, is actually quite small, measured in hundredths of an arcsecond. But it's enough to create visible color effects, especially when combined with the intensity fluctuations we discussed earlier. When the atmosphere focuses blue light toward your eye while simultaneously defocusing red light away, you see a blue flash. Moments later, the situation reverses, and you see a red flash. There's another optical effect at play here, one that's more subtle but equally important: diffraction. When light passes through a small aperture or around an obstacle, it spreads out. This is diffraction, a wave property of light. In the atmosphere, when turbulent cells become small enough, comparable to the wavelength of light itself, or just a few thousand nanometers across, diffraction effects become significant. These tiny turbulent cells act like microscopic lenses and apertures, creating complex diffraction patterns. The interaction between refraction from larger-scale turbulence and diffraction from microscopic turbulence creates the full complexity of stellar scintillation. It's a multi-scale phenomenon, with physics at different size scales all contributing. Let me share a specific historical example that illustrates how precisely scientists have learned to measure and understand refraction in the atmosphere. In 1716, Edmund Halley, yes, the same Hawley of Halley's Comet fame, carefully measured the position of stars near the horizon and compared them to the known positions of the same stars when high in the sky. He found that stars near the horizon appeared displaced upward by about half a degree, 30 arc minutes. This displacement is pure atmospheric refraction. Light from stars near the horizon passes through so much atmosphere and encounters such a large cumulative change in refractive index from the top of the atmosphere to sea level that it bends significantly. The stars appear higher in the sky than they geometrically should be. Halley's measurements were remarkably accurate. Modern calculations using detailed models of Atmospheric density and temperature profiles predict almost exactly the displacement Halley measured 3 centuries ago. But Halley was measuring the steady-state refraction, the average bending caused by the average atmosphere. The rapid fluctuations around that average, the twinkling, required faster measurements and more sophisticated instruments to study. In the 20th century, with the development of fast photodetectors and computers, astronomers could finally measure scintillation in detail. They could track how brightness varied over time, could measure the spectrum of colors during scintillation, could correlate atmospheric conditions with scintillation intensity. What emerged was a detailed quantitative understanding of how turbulence creates twinkling through refraction. One particularly elegant set of experiments was conducted at the Mount Wilson Observatory in California during the 1950s and 60s. Astronomers set up multiple telescopes separated by various distances, some just a few feet apart, some hundreds of feet apart. They observed the same star simultaneously through all telescopes and compared how the scintillation patterns correlated. What they found was striking. Telescopes very close together saw nearly identical scintillation patterns. The same brightenings and dimmings occurred at the same times, but telescopes separated by more than a few feet saw increasingly different patterns. Beyond about 30 feet of separation, the scintillation patterns were essentially uncorrelated. Each telescope was seeing starlight that had passed through different turbulent cells. This told astronomers the typical size of turbulent cells in the atmosphere above Mount Wilson, about 20 to 40 feet across. Different observatories under different atmospheric conditions measured different characteristic sizes, but the principle held everywhere. There's a spatial scale to atmospheric turbulence, a typical size of refractive structures, and that size determines how scintillation appears and how it affects telescopes of different apertures. Large telescopes actually have an advantage when it comes to scintillation. A large mirror collects light from a patch of sky large enough to encompass many turbulent cells. Some cells might be defocusing light, but others might be focusing it. The effects partially average out. The star still appears to shimmer, but the rapid intensity fluctuations are somewhat reduced compared to what a smaller telescope would see. This is called aperture averaging, and it's one reason why professional astronomers prefer large telescopes, even for applications where light gathering power isn't the primary concern. There's an almost poetic aspect to all of this. Light from a star, photons that have traveled for years or centuries through empty space, maintaining perfect coherence and direction, arrives at Earth only to have its final mile of journey scrambled by air. Tiny temperature differences of a few degrees, turbulent eddies no bigger than a person, refractive indices differing by a few parts per million. These small, almost negligible effects completely transform the appearance of starlight. And yet, the light itself carries no memory of this journey. If you could somehow catch an individual photon after it passed through the atmosphere and ask it about its journey, you'd find it unchanged. Photons don't get tired or worn out by passing through turbulent air. They just follow the rules, traveling in straight lines through uniform medium, bending according to Snell's law when they encounter boundaries, maintaining their energy and wavelength. The complexity of twinkling emerges not from complex behavior of individual photons, but from the statistical aggregate of billions of photons taking slightly different paths through a constantly changing medium. This is a profound point that's worth sitting with for a moment. The shimmer of starlight isn't a property of light itself. It's a property of the medium light travels through. Change the medium, and the shimmer vanishes. This suggests something we'll explore more deeply later. If we could observe stars from above the atmosphere, they wouldn't twinkle at all. They'd shine with perfect, unwavering steadiness. Astronauts in space see exactly this. Stars that don't shimmer, that appear as hard, steady points of light. But even understanding refraction and its effects on intensity doesn't tell the complete story. Because twinkling isn't just about brightness variations. Stars also appear to change color as they twinkle, sometimes dramatically. And they seem to shift position, to dance slightly in the sky. These additional phenomena, chromatic changes and positional wandering, add layers of complexity to the story of stellar scintillation. They reveal even more about how light interacts with our atmosphere, about the deep connection between color, wavelength, and refraction. On a cold January night in 1844, a British astronomer named William Lassell was observing Sirius through his telescope when something extraordinary happened. The brilliant star began to flash, not just brightening and dimming, but cycling through colors: electric blue, pure white, deep red, even what he described as emerald green. The display was so dramatic that Lassell initially wondered if his telescope optics were damaged. But when he looked at other stars, they appeared normal. Only Sirius was performing this chromatic dance. What Lassell was witnessing wasn't a defect, and it wasn't the star changing. He was seeing the full complexity of atmospheric scintillation, a phenomenon that involves not just brightness variations, but color changes and positional shifts happening simultaneously, painting one of nature's most intricate optical performances. If you're captivated by these details of how the universe reveals itself to us, A-Like helps share this wonder with others. And subscribing ensures you'll be here for every discovery we uncover together. Thank you. Let's unpack what's really happening when a star twinkles. We've established that atmospheric turbulence bends light through refraction, and that this bending can focus or defocus light, causing brightness variations. But twinkling has three distinct components working together: changes in position, changes in intensity, and changes in color. Each component tells us something different about the physics at play, and together they create the complete phenomenon we observe. Start with positional scintillation, the apparent movement of a star's position in the sky. When turbulence bends light, it doesn't just change how much light reaches us, it also changes the direction from which that light appears to come. A turbulent cell acting as a temporary prism might bend light 5/1000ths of an arcsecond to the left. A moment later, different turbulence might bend it 3/1000ths of an arcsecond to the right. The star appears to dance around its true position. These movements are tiny, typically just a few hundredths of an arcsecond, far too small to see with the naked eye. But telescopes can detect them, and they cause problems for precise astronomical work. When you're trying to measure the exact position of a star to track its motion through the galaxy, atmospheric scintillation introduces noise, random apparent movements that have nothing to do with the star's actual motion. In 1838, Friedrich Bessel made the first successful measurement of stellar parallax, the apparent shift in a star's position as Earth orbits the Sun, which finally allowed astronomers to measure the distance to nearby stars. Bessel chose 61 Cygni, a relatively faint star, for his landmark measurement. One reason he chose this particular star was its high position in the sky, as seen from his observatory in Königsberg, Prussia. High overhead, atmospheric scintillation was minimized, making position measurements more reliable. Even so, Bessel had to average hundreds of observations to overcome the random positional variations caused by atmospheric turbulence. This illustrates an important point. Atmospheric scintillation isn't just an aesthetic phenomenon. It's a practical limitation on astronomical precision. Every position measurement, every brightness measurement, every spectrum includes noise from atmospheric effects. Modern astronomers have developed sophisticated techniques to minimize this noise, but it's always there, always limiting what we can measure from the ground. Now, let's explore intensity scintillation more deeply than we have before. The brightness variations aren't symmetrical. Stars don't spend equal time being brighter and dimmer than average. The distribution is skewed. Most of the time, turbulence spreads light out, making stars appear slightly dimmer than their average brightness. Occasionally, turbulence focuses light, producing brief, bright flashes. Mathematically, this creates what's called a log-normal distribution of intensity. If you measured the brightness of a twinkling star thousands of times per second and plotted the results, you'd see a characteristic curve, a peak at slightly below average brightness, a long tail extending toward high brightness, and a sharp cutoff preventing brightness from dropping below zero. This distribution shape is a signature of multiplicative random processes, situations where the outcome at each step depends on multiplying by random factors. Atmospheric refraction through multiple turbulent layers is exactly this kind of process. The strength of scintillation, how much stars vary in brightness, depends on several factors we can quantify precisely. One is the zenith angle, how far the star is from directly overhead. Remember, stars near the horizon pass through much more atmosphere. A star at 60 degrees from zenith, 30 degrees above the horizon, passes through twice as much atmosphere as a star directly overhead. The scintillation strength scales approximately with the square of this increased path length. So, a star at 60 degrees from zenith shows about 4 times stronger scintillation than the same star overhead. Another factor is the wavelength of light. Blue light scintillates more strongly than red light. This isn't obvious from casual observation because our eyes integrate over time and don't perceive rapid fluctuations well. But instruments can measure it precisely. Blue light, with its shorter wavelength, is more strongly affected by small-scale atmospheric turbulence. The difference is about 30%. Blue light shows roughly 30% stronger intensity variations than red light under the same conditions. This wavelength dependence becomes crucial when we talk about chromatic scintillation, color changes. White light from stars is a mixture of all visible wavelengths. When turbulence refracts this light, different wavelengths bend by different amounts. We discuss this in terms of dispersion, but let's now explore the consequences more fully. Imagine a turbulent cell that acts as a weak prism, spreading white light into a tiny spectrum. The blue light bends slightly more than the red light. They separate by perhaps a few hundredths of an arc second. Now, if your eye or telescope happens to be positioned where it catches more of the blue light and less of the red light from this separation, the star appears blue-tinted. A moment later, the turbulence shifts, and now you're catching more red light than blue light. The star appears red-tinted. These color shifts happen rapidly, often 10 to 50 times per second, creating the characteristic color flashing visible in bright stars. Sirius is the champion of this effect because it combines 3 factors. It's extremely bright, making the colors visible. It's often low in the sky for observers in the northern hemisphere, increasing atmospheric path length. And it's blue-white to begin with, providing strong emission across the entire visible spectrum. Let me share a specific observation that illustrates this beautifully. In December 1985, astronomer Stephen O'Meara, observing from Mount Palomar in California, used a special instrument called a multi-channel photometer to measure Sirius's brightness in 6 different color bands simultaneously, with a time resolution of 1/100th of a second. What he found was remarkable. The color fluctuations weren't random. When Sirius brightened in blue light, it often simultaneously dimmed in red light, and vice versa. The turbulence wasn't just scattering light randomly, it was actively splitting the spectrum, sending different colors in different directions. O'Meara's measurements also revealed the timescale structure of chromatic scintillation. The color changes occurred primarily on timescales of 0.02 to 0.05 seconds, 20 to 50 times per second. This corresponds to the time it takes for atmospheric turbulent cells about 1 to 2 feet across to move across the line of sight at typical wind speeds of 20 to 40 miles per hour. These numbers connect atmospheric physics, wind speed, and turbulent cell size directly to observable optical phenomena. There's an interesting historical footnote here. In ancient and medieval times, different civilizations attributed meaning to the colors of stars. Some stars appeared red, some blue, some yellow, but bright stars near the horizon often seemed to cycle through multiple colors. This led to some confusion in historical star catalogs. Was a star's true color the one seen when it was overhead, or the colors it showed near the horizon? The answer, of course, is that stars have intrinsic colors based on their surface temperature. Red stars are cooler, blue stars are hotter. But these intrinsic colors get overlaid with chromatic scintillation effects when viewed through Earth's atmosphere. Distinguishing between intrinsic stellar color and atmospheric color effects was an important step in the development of astrophysics in the late 19th century. Now, let's talk about a common misconception that persists even today. Many people assume that twinkling occurs because of clouds or water vapor in the atmosphere. It's easy to see why. Humid nights often show more dramatic twinkling, and we associate water vapor with optical effects like rainbows and halos. But this is misleading. Water vapor itself isn't the cause of twinkling. The refractive index of humid air is actually slightly lower than dry air. Water molecules are lighter than nitrogen and oxygen molecules, so water vapor is less dense. What matters is that conditions producing high humidity, warm air holding moisture, fronts where air masses mix, instability in the atmosphere, also tend to produce turbulence and temperature variations. It's the turbulence, not the humidity per se, that causes twinkling. This misconception led early meteorologists astray when they tried to correlate twinkling with weather conditions. In the 1870s, several European observatories attempted to use stellar scintillation as a predictor of upcoming weather. The logic seemed sound. If twinkling indicated atmospheric conditions, perhaps those conditions could predict weather changes. But the correlations were weak and unreliable. Twinkling tells you about atmospheric turbulence at the moment, primarily in the upper atmosphere, but it doesn't reliably predict what weather will do hours or days later. The atmosphere is too complex, with too many independent variables. However, there is one weather correlation that does hold: the passage of high-altitude jet streams. When a strong jet stream passes over an observatory, scintillation typically increases noticeably. The jet stream creates shear, sharp boundaries between fast-moving and slower-moving air, and this shear generates turbulence. Astronomers learned to avoid critical observations on nights when strong jet streams were forecast overhead. This practice continues today at professional observatories worldwide. Let's explore one more aspect of intensity scintillation: saturation. You might expect that increasing atmospheric turbulence would continuously increase scintillation strength, more turbulence, more twinkling. But this isn't quite true. Beyond a certain level of turbulence, scintillation strength actually plateaus. This is called the strong scintillation regime. What happens is this: in mild turbulence, starlight maintains some coherence. The light waves stay partially synchronized with each other. In strong turbulence, this coherence is completely destroyed. The light from different parts of a star's image becomes completely randomized. At this point, adding more turbulence doesn't make things worse. They're already maximally scrambled. The scintillation reaches a ceiling. This saturation was first clearly observed and explained in the 1970s by Russian physicist Vladimir Tatarsky, who developed the mathematical theory of wave propagation through turbulent media. Tatarsky showed that scintillation strength increases roughly proportional to turbulent strength in weak turbulence, but then follows a more complex relationship in strong turbulence, eventually reaching a maximum value beyond which further turbulence has little additional effect. For practical observing, this means that truly terrible seeing conditions aren't much worse than merely bad conditions when it comes to scintillation. Both scramble the light completely. The real difference between bad and good conditions is the size of the turbulent cells and the resulting image blur, not necessarily the intensity variations. There's a seasonal pattern to scintillation intensity that amateur astronomers learn through experience. Summer nights often show stronger scintillation than winter nights, particularly for stars viewed in the early evening. Why? During summer, the ground absorbs heat all day, and after sunset, that heat continues to radiate upward, creating thermal turbulence near the surface. In winter, the ground cools quickly after sunset, reducing thermal turbulence. The atmosphere becomes stratified and more stable. But there's a catch. Winter brings stronger jet streams, which create high-altitude turbulence. So, the seasonal difference is most noticeable for stars viewed at moderate elevations. Stars directly overhead may show similar scintillation year-round, while stars 30 degrees above the horizon show much stronger summer scintillation. Experienced observers know this and plan their observations accordingly. Let me share a practical example of how scintillation affects real astronomical work. In 1992, astronomers using the Hubble Space Telescope were preparing to observe supernova 1987A in the Large Magellanic Cloud. They needed to coordinate Hubble observations with ground-based observations from several observatories to cover multiple wavelengths simultaneously. The ground-based observations require precise photometry, brightness measurements accurate to a few percent. The problem was scintillation. Even with large telescopes and averaging over exposure times of several minutes, scintillation from Earth's atmosphere introduced brightness variations of 3 to 5%, comparable to the precision they needed. To overcome this, the observatories took many repeated measurements and used statistical techniques to separate real brightness changes in the supernova from atmospheric scintillation noise. It worked, but it required far more observing time than would have been needed without atmospheric effects. This brings us to an important realization. Scintillation isn't just an interesting phenomenon to explain. It's a fundamental limitation on ground-based astronomy. Every brightness measurement from the ground includes atmospheric noise. Every spectrum has scintillation-induced variations overlaid on the true stellar spectrum. Every high-resolution image is degraded by atmospheric effects. Understanding scintillation in detail, knowing that it has three components, knowing how it scales with wavelength and zenith angle, knowing its time scales and statistical properties, allows astronomers to work around it, to design better instruments and observing strategies. But there's always a price paid. Ground-based astronomy is fundamentally constrained by Earth's atmosphere. This raises an intriguing question. If stars themselves don't twinkle, if the phenomenon is entirely atmospheric, what would stars look like from above the atmosphere? If you could somehow float in space, looking at stars without any air between you and them, would they appear different? The answer is profound and perhaps surprising. Astronauts who have spent time in space consistently report that stars look different, clearer, steadier, somehow more real than they appear from Earth's surface. But there's something else they report too. Stars in space look colder, more distant, less alive. The twinkling we see from Earth, even though it's an atmospheric effect, somehow makes stars feel more present, more connected to us. But we're getting ahead of ourselves. Before we explore how stars appear from space, we need to solve another puzzle, one that ancient astronomers noticed but couldn't explain. Why do some celestial objects twinkle while others remain steady? Why do planets shine with unwavering light while stars dance and shimmer? Go outside tonight when Venus is visible, that brilliant point of light that outshines everything except the sun and moon. Watch it for a few minutes. You'll notice something remarkable. It doesn't twinkle. It shines with steady, unwavering light, even when it's low on the horizon where stars would be flashing and shimmering wildly. Ancient astronomers noticed this thousands of years ago, and it puzzled them deeply. Venus passes through the same turbulent atmosphere as starlight. It encounters the same refractive cells, the same temperature variations, the same turbulence. So, why does Venus remain calm while stars dance? The answer reveals something profound about how our brains perceive light, about the physical size of objects in the sky, and about why the distinction between planets and stars was one of humanity's first great astronomical insights. If these cosmic revelations bring you a sense of wonder, I'd be deeply grateful for your like and subscription. It's how these stories reach others who might need them. Thank you for being part of this journey. The key to understanding why planets don't twinkle lies in a single concept: angular size. This is the apparent diameter of an object as seen from your position, how much of your field of view it occupies. Angular size is measured in degrees, arc minutes, or arc seconds. The full moon, for comparison, has an angular diameter of about 30 arc minutes, or half a degree. Stars, even the closest ones, are so incredibly far away that they appear as true points of light. They have essentially zero angular size. Even through the most powerful telescopes on Earth, stars remain points. They're so distant that their actual physical diameter, even though stars are enormous objects, subtends an angle far too small to resolve. Sirius, the brightest star in our night sky, is about 8.6 light-years away. Its actual diameter is 1.5 million miles, nearly twice the diameter of our Sun. And yet, from Earth, Sirius has an angular diameter of only 0.06 arcseconds. That's far below what any telescope on Earth's surface can resolve through atmospheric turbulence. Planets are different. They're much, much closer. Venus, at its nearest approach to Earth, is only about 25 million miles away, roughly 1,400 times closer than the nearest star beyond our Sun. And although planets are much smaller than stars in actual physical size, their proximity makes them appear larger in angular terms. Venus, when closest to Earth, has an angular diameter of about 60 arcseconds, 10,000 times larger than Sirius. Jupiter, the largest planet, can appear 45 arcseconds across. Even Mars, which is smaller, shows an angular diameter of about 25 arcseconds during favorable oppositions. Here's why this matters for twinkling. Remember that atmospheric turbulence creates cells of air with different refractive properties. These cells are typically 1 to 3 feet across as seen from the ground. When starlight, arriving from a single point, passes through one of these cells, all the light from that star encounters the same refractive cell simultaneously. If the cell bends light to the left, the entire star image shifts left. If the cell focuses light, the entire star brightens. If the cell disperses light, the entire star dims. The star responds as a unit to each turbulent cell it encounters. But planets present an extended disk, not a point. Even though that disk is small, just 10 to 60 arcseconds, it's large enough to span multiple turbulent cells in the atmosphere. Different parts of the planet's disk have their light passing through different turbulent cells. Some cells might be focusing light from the left edge of the planet, while other cells are defocusing light from the right edge. Some cells might bend light from the top of the planet to the left, while others bend light from the bottom to the right. The crucial point is this: these effects average out. When your eye or telescope collects all the light from the planet's disk, it's combining light that has passed through many different turbulent cells, each doing something slightly different. The brightening in one part of the image cancels the dimming in another part. The leftward shift in one region cancels the rightward shift in another. The result is steady, averaged light, no perceptible twinkling. This averaging effect is spatial. It happens across the extended disk of the planet. It's fundamentally different from the temporal averaging that occurs when you observe anything for a long time. Temporal averaging could, in principle, smooth out twinkling from stars if you watch for long enough. But spatial averaging is instantaneous. At every moment, the planet's light is already averaged over multiple turbulent cells. Let me make this more concrete with actual measurements. Imagine observing Jupiter through moderate atmospheric turbulence, where the typical turbulent cell is about 1 foot across as projected onto the ground. Jupiter's angular diameter is about 45 arcseconds. At typical atmospheric heights where turbulence occurs, let's say 15,000 feet, those turbulent cells project to about 2 arcseconds across, as seen by someone on the ground, looking up through them at that altitude. Jupiter's disk of 45 arcseconds therefore spans roughly 22 turbulent cells from edge to edge. Light from one side of Jupiter passes through completely different turbulence than light from the other side. With 22 independent turbulent cells being averaged together, the random brightness fluctuations reduce by a factor of roughly the square root of 22, or about 4.7. The twinkling becomes 5 times weaker than it would be for a point source. But that's not the whole story. The distribution of light across a planet's disk isn't uniform. The center is usually brighter than the edges, due to limb darkening and viewing geometry. This means the effective averaging is somewhat less than you'd calculate from a simple geometric model. Still, for planets like Jupiter, Venus, and Mars, the averaging is strong enough that twinkling becomes imperceptible to the human eye under most conditions. There are exceptions, though. When planets are very low on the horizon, within 5 degrees or so, they can show slight twinkling or shimmering. The atmospheric path length is so extreme that even spatial averaging can't completely eliminate scintillation effects. Additionally, when planets are at their most distant from Earth, their angular size shrinks. Mars at aphelion, its farthest point from both the Sun and Earth, can appear as small as 4 arcseconds. At that size, Mars begins to twinkle slightly, particularly when low on the horizon. Mercury presents an interesting case. It's always close to the Sun, which means it's always observed relatively low on the horizon during twilight, when the atmosphere tends to be turbulent from daytime heating. Mercury also has a small angular size, typically 10 arcseconds or less. The combination means Mercury sometimes shows noticeable twinkling, more than any other planet. Ancient astronomers sometimes classified Mercury's behavior as intermediate between stars and planets because of this. The Moon, of course, never twinkles. With an angular diameter of 30 arc-minutes, 1,800 arc-seconds, the Moon spans roughly 900 turbulent cells. The averaging is so complete that scintillation is utterly eliminated. Even more interesting, the Moon is large enough that you can sometimes see atmospheric effects at its edge. The limb appears to shimmer slightly during very poor seeing, but the overall disk remains steady. This distinction between twinkling stars and steady planets was crucial in the development of astronomy. Ancient observers knew that 5 celestial objects, Mercury, Venus, Mars, Jupiter, and Saturn, behaved differently from the fixed stars. They called them wanderers because they moved against the background of stars. But they also noticed the steady versus twinkling distinction, even though they didn't understand the cause. In ancient Greek astronomy, This difference contributed to the philosophical separation between the celestial spheres of planets and the celestial sphere of fixed stars. Planets occupied inner spheres, closer to Earth, which explained why they moved against the background stars. The fact that they didn't twinkle was noted but not explained. Aristotle and others simply accepted it as another property of the celestial bodies without understanding the mechanism. The geocentric model of Ptolemy, which dominated astronomy for 1,400 years, placed planets in order by their apparent motions: Moon, Mercury, Venus, Sun, Mars, Jupiter, Saturn, with fixed stars beyond. This ordering happened to be correct in terms of distance, except for the Sun and its relationship to Venus and Mercury, though Ptolemy didn't have any distance measurements. The lack of twinkling in planets was consistent with them being closer, but again, the mechanism wasn't understood. When Copernicus proposed the heliocentric model in 1543, placing the Sun at the center and Earth as a planet orbiting it, the twinkling distinction remained relevant. Stars still twinkled and planets didn't, which was now explained by stars being vastly more distant than planets, though Copernicus couldn't measure these distances. He simply reasoned that if Earth orbits the Sun and we see no parallax in stars, no apparent shift in their positions over the course of a year, then stars must be extraordinarily far away. The invention of the telescope in 1608 and Galileo's astronomical observations beginning in 1609 added new dimension to this puzzle. Through a telescope, stars remained points of light. They showed no disks, no visible surface features. Galileo found this mysterious. Why couldn't telescopes magnify stars into visible disks the way they magnified planets? The answer, which wasn't fully understood until the development of optics as a science, is that stars genuinely have zero angular size as seen from Earth, or rather, an angular size far smaller than atmospheric turbulence and optical diffraction effects allow us to resolve. Planets, even through modest telescopes, showed visible disks. Galileo could see phases of Venus, moons of Jupiter, rings of Saturn, though he misinterpreted them at first. These were clearly extended objects. Stars remained point-like no matter the magnification. This telescopic observation reinforced what naked-eye observers had noted about twinkling. Planets were fundamentally different from stars in both nature and distance. The twinkling distinction was one piece of evidence among many that helped establish the true structure of the solar system and the vast scale of the universe beyond. Now, let's talk about artificial satellites, because they present an interesting intermediate case. A satellite in low Earth orbit, say the International Space Station, is typically 200 to 400 miles away. Its actual physical size might be over 300 feet across, giving it an angular size of about 30 to 60 arcseconds when directly overhead, comparable to planets. But satellites tumble, rotate, and have irregular shapes with flat reflective surfaces. The sunlight glinting off a solar panel can come from essentially a point-like source, a specular reflection. When that happens, the light twinkling, satellites often appear to flash or pulsate as they cross the sky, and part of this is genuine brightness variation from their changing orientation. But part of it is also scintillation of the reflected sunlight, which behaves more like a point source than an extended disk. The Starlink satellites that SpaceX has been launching since 2019 provide a modern example. These satellites are small, about the size of a table, and orbit at about 340 miles altitude. When they catch the sun just right, they can be quite bright, but their angular size is tiny, well under 1 arcsecond. They twinkle noticeably, behaving more like bright stars than like planets, despite being far closer than any planet. There's another special case worth discussing: asteroids. Most asteroids are too faint to see with the naked eye, but the brightest Vesta can reach magnitude 5.5, just barely visible without optical aid in dark skies. Vesta's angular diameter is less than 1 arcsecond. It appears point-like even through large telescopes. Despite being a solar system object, closer than the stars, Vesta twinkles because its angular size is too small for spatial averaging to work. It behaves like a star, not like a planet. This illustrates the key principle. It's not about whether an object is intrinsically a planet or a star. It's purely about angular size as seen from Earth. Any object, regardless of what it is, will twinkle if its angular size is below a certain threshold, where spatial averaging becomes ineffective, and will shine steadily if its angular size is above that threshold. That threshold depends on atmospheric conditions. In very calm air with large turbulent cells, the threshold might be 2 to 3 arcseconds. In highly turbulent air with small turbulent cells, the threshold might be as high as 10 arcseconds. This means that Mars, during periods when its angular diameter is 4 to 5 arcseconds, might show slight twinkling on turbulent nights, but appear steady on calm nights. The planet hasn't changed, the atmosphere has. Amateur astronomers sometimes use this as a practical tool. When planning to observe planets with a telescope, they'll look at bright stars to judge the seeing conditions. If stars are twinkling wildly, planetary observations will be difficult. The atmospheric turbulence will blur fine details. If stars show minimal twinkling, it's a good night for planetary work. Professional astronomers at observatories use more quantitative methods, but the principle is the same. Stellar scintillation measurements provide real-time information about atmospheric turbulence conditions, which can guide decisions about what to observe and how to configure instruments. There's a beautiful irony here. Stars, distant suns, some hundreds or thousands of times larger than Jupiter, appear as mathematical points and dance in Earth's atmosphere. Planets, tiny worlds, rocky or gaseous, dwarfed by stars, appear as extended disks large enough to suppress atmospheric scintillation. Proximity wins over intrinsic size. The nearby small object presents a larger angular face than the distant giant. This same principle applies throughout astronomy. The angular size of an object, not its actual physical size, determines how it appears and how atmospheric effects influence it. A galaxy might contain hundreds of billions of stars and span 100,000 light-years. But if it's hundreds of millions of light-years away, it might present a smaller angular size than Jupiter. That galaxy won't twinkle either, not because it's a galaxy, but because its extended angular size allows spatial averaging of atmospheric effects. Consider for a moment what this means for our perception of the universe. The celestial objects that appear most stable, most permanent to our eyes, the planets and moon, are actually the nearest, the most accessible. The objects that seem most ethereal, most changeable, the twinkling stars, are vastly more distant, separated from us by distances so great that light takes years or centuries to cross them. Our atmosphere creates an inverted sense of permanence and transience. Ancient peoples often associated planets with gods: Jupiter, Venus, Mars, Saturn, Mercury, partly because of their steady, unwavering light. Stars were perhaps souls or distant lamps or holes in the celestial sphere. The phenomenological difference, the twinkling versus steady distinction, led to different mythological and philosophical categorizations. Human attempts to understand the cosmos were shaped in part by this optical effect, by how Earth's atmosphere selectively scrambles light based on angular source size. Have you ever looked at Venus and wondered what it would be like to see stars shine with that same steady clarity? To observe the entire night sky rendered as calmly as planets appear? Such a view is possible, but it requires leaving Earth's atmosphere behind entirely, rising above the turbulent ocean of air that has shaped humanity's view of the stars since our species first looked up at the night sky. That journey beyond the atmosphere reveals not just steady starlight, but an entirely transformed cosmos, simultaneously clearer and more alien than anything visible from the ground. On July 20th, 1969, Neil Armstrong and Buzz Aldrin stood on the moon's surface, surrounded by absolute silence and airless vacuum. When they looked up at the sky, even during what we would call daytime on the moon, they could see stars. But these stars looked different from any stars they had ever seen from Earth. In the mission transcripts, Aldrin described them as appearing hard and brilliant, steady, unwavering points of light that seemed almost artificial in their constancy. Armstrong noted that the stars looked colder somehow, more distant. Neither astronaut was quite prepared for how unsettling it would be to see stars that didn't twinkle. The gentle shimmer we take for granted from Earth's surface, that quality that makes stars seem alive, almost breathing, was completely absent. The stars shone with perfect, almost harsh steadiness. And in that steadiness, humanity glimpsed for the first time what the universe actually looks like without the filter of our atmosphere. If these moments of cosmic discovery move you, I'd be honored if you'd leave a like and subscribe. It's your support that allows these stories to reach others searching for the same wonder. Thank you. Let's explore what happens when you remove atmosphere from the equation entirely. Every human who has traveled beyond Earth's atmosphere, astronauts, cosmonauts, taikonauts, reports the same observation. Stars don't twinkle in space. They shine with absolute steadiness. This isn't a subtle difference. It's dramatic, even jarring to observers who spent their entire lives seeing twinkling stars from Earth's surface. The reason is straightforward. No atmosphere means no turbulence, no refractive cells of varying density, no medium to bend and scatter starlight. Light from stars travels through the vacuum of space and enters an astronaut's eye or a spacecraft's telescope, without passing through any material that could alter its path. The result is pure, unwavering illumination. But let's go deeper into what this actually means for astronomy, because the implications are profound. The Hubble Space Telescope, launched in 1990 and still operational today, orbits Earth at about 340 miles altitude, well above 99.9% of the atmosphere. Hubble's mirror is 7.9 feet in diameter, not particularly large by modern ground-based standards. Many ground-based telescopes have mirrors 2 or 3 times larger, yet Hubble consistently produces sharper, clearer images than any ground-based telescope could achieve before the development of adaptive optics in the 1990s. Why? Because Hubble doesn't have to contend with atmospheric turbulence. When Hubble points at a star, it sees a perfect point source, limited only by the fundamental physics of diffraction, the unavoidable spreading of light waves that occurs when they pass through any aperture. The images Hubble produces have angular resolution of about 0.05 arcseconds, meaning it can distinguish features in space separated by just 5/100ths of an arcsecond. Compare this to ground-based telescopes before adaptive optics. Even at the best observing sites, on the calmest nights, atmospheric turbulence limited resolution to about 0.5 to 1.0 arcsecond, 10 to 20 times worse than Hubble, even for telescopes with much larger mirrors. The atmosphere was stealing resolution, blurring images that should have been sharp, mixing light from adjacent stars that should have been separately resolved. Let me give you a concrete example of what this difference means. In 1994, astronomers using ground-based telescopes had been observing the globular cluster M15 for decades. Globular clusters are dense balls of hundreds of thousands of stars, all orbiting together. The cores of these clusters are incredibly crowded, stars packed so densely that, from our distant viewpoint, they blur together into an unresolved glow. When Hubble pointed at M15, it revealed individual stars in the core that had never been distinguished before. Features that appeared as a smooth, featureless blob from the ground resolved into hundreds of separate stellar points. It was like cleaning a dirty window and suddenly seeing a landscape you knew was there, but had never actually glimpsed clearly. The stars were always there, always separate, but Earth's atmosphere had been mixing their light together, making them appear as an undifferentiated glow. This resolution advantage affects almost every area of astronomy. Binary stars, pairs of stars orbiting each other, that appear as single points from the ground, can be resolved as separate objects from space. Galaxies that look like smooth ellipses from ground-based telescopes reveal intricate structure, spiral arms, dust lanes when observed with Hubble. Planets around other stars, which cast incredibly tiny shadows and create minuscule brightness variations in their parent stars, become detectable when you eliminate atmospheric scintillation noise. But there's another advantage beyond resolution: photometric precision. Remember, atmospheric scintillation causes stars to vary randomly in brightness by a few percent, sometimes more. This variation is noise for astronomers trying to measure genuine brightness changes in stars, variations caused by stellar pulsation, by planets transiting in front of the star, by binary companions periodically eclipsing each other. From space, this noise vanishes. Brightness measurements can achieve precision of parts per million, far better than anything achievable from the ground without extensive averaging. This precision revolutionized the search for exoplanets. The Kepler Space Telescope, launched in 2009 specifically to search for planets around other stars, monitored 150,000 stars continuously for 4 years, measuring their brightness with precision of 20 parts per million. When a planet passes in front of its star, as seen from our viewpoint, it blocks a tiny fraction of the star's light, perhaps 1% for a large planet, as little as 0.01% for an Earth-sized planet. Kepler could detect these tiny dips in brightness because it operated in space, above atmospheric scintillation. Kepler discovered over 2,600 confirmed exoplanets. Many of these planets would have been impossible to detect from ground-based telescopes, not because ground-based telescopes lack sensitivity, but because atmospheric scintillation would have buried the planetary signal in noise. Removing atmospheric twinkling didn't just improve astronomy, it opened entirely new research areas. The astronauts who experienced this transformation firsthand often struggled to articulate what it felt like. Let me share some specific accounts because they're remarkably consistent and deeply revealing. Soviet cosmonaut Alexei Leonov, who performed the first spacewalk in 1965, later described looking at stars during his time outside the spacecraft. He noted that stars appeared absolutely motionless and diamond-like. His impression was that they looked more like artificial lights than natural celestial objects. The lack of twinkling made them seem manufactured, precise, cold. American astronaut Alan Bean, who walked on the moon during Apollo 12 in 1969, described a similar experience. In interviews decades later, he recalled being struck by how still the stars were, and how this stillness made the lunar environment feel even more alien and lifeless. On Earth, the twinkling of stars creates a sense of dynamism, of change, of life in the sky. On the moon, the sky felt frozen, static despite the actual motions of stars across the heavens as the moon rotated. Commander Eugene Cernan, the last human to walk on the moon during Apollo 17 in 1972, reported perhaps the most poetic description. He said the stars from the moon looked too perfect, and that this perfection was somehow unsettling. He'd spent his entire life seeing stars twinkle, and the absence of that familiar behavior made the universe feel less welcoming, more distant and indifferent. These psychological reactions tell us something profound about how deeply the twinkling of stars is embedded in human experience. For our entire evolutionary history, every human who ever looked at the night sky saw twinkling stars. It's part of our baseline expectation of what the universe looks like. When that expectation is violated, when stars become steady, even trained astronauts and pilots experience a sense of cognitive dissonance, a feeling that something is wrong or unnatural. But from a purely scientific perspective, steady starlight is correct, and twinkling is the distortion. Stars themselves are stable light sources, or at least far more stable than the atmosphere makes them appear. The twinkling we see from Earth is noise, interference added by our planet's shell of air. Space telescopes and astronauts see what's actually there, the universe as it is, not as it appears through atmospheric turbulence. This raises an interesting question. If we've only been able to observe stars without atmospheric interference since the 1960s, how did astronomers manage before then? The answer is through painstaking work, statistical averaging, careful site selection, and acceptance of fundamental limitations. Pre-space age astronomers developed sophisticated techniques to work around atmospheric effects. They took many repeated observations and averaged them, trading time for precision. They built observatories on high mountains where the atmosphere was thinner and calmer. They specialized in areas of astronomy where atmospheric effects were less critical. Spectroscopy, which analyzes the colors of light and can tolerate some scintillation noise, or photography, with very long exposures that average out short-term variations. But there were things they simply couldn't do. High-resolution imaging of fine details in planets, galaxies, and nebulae was fundamentally limited by atmospheric seeing. Precise brightness measurements of variable stars were always contaminated by scintillation noise. Searches for faint objects near bright stars were frustrated by scattered light from atmospheric effects. These limitations weren't just inconveniences. They defined the boundaries of what astronomy could achieve from the ground. The decision to place telescopes in space was expensive and technologically challenging, but it was driven by a clear recognition that some observations were impossible from Earth's surface, no matter how large the telescope or how sophisticated the instruments. The atmosphere was an insurmountable barrier for certain types of work. Hubble's launch in 1990 initially appeared to be a disaster. The telescope's primary mirror had been ground to the wrong shape, a spherical aberration that blurred images severely. This manufacturing error, just 1/50th the width of a human hair in magnitude, was catastrophic for image quality. But even with this flaw, Hubble's images from space were still competitive with ground-based telescopes because it didn't suffer from atmospheric turbulence. The mirror error affected all light equally and predictably, while atmospheric turbulence was random and unpredictable. After astronauts installed corrective optics in 1993, Hubble achieved its full potential, and the difference was stunning. One of the most famous Hubble images illustrates this perfectly. The Pillars of Creation in the Eagle Nebula, captured in 1995. These towering columns of gas and dust, light years tall, were known to exist from ground-based observations. But ground-based images showed them as fuzzy, indistinct structures. Hubble revealed intricate detail, delicate wisps of gas, sharp boundaries between bright and dark regions, individual stars forming inside the pillars. The nebula itself hadn't changed. The difference was purely in how clearly we could see it without atmospheric interference. The James Webb Space Telescope, launched in 2021, took this even further. Webb operates at infrared wavelengths, which penetrate dust that obscures visible light. But Webb also benefits from being in space. No atmospheric absorption of infrared light, no thermal emission from warm atmosphere, no turbulence to blur images. Webb's mirror is 21.3 feet across, nearly 3 times the diameter of Hubble's mirror, giving it 6 times the light-gathering power and much finer angular resolution at its operating wavelengths. Early Webb images, released in 2022, showed galaxies from the early universe with clarity that left astronomers stunned. Features that were barely detected smudges in Hubble images appeared as detailed structures in Webb images. Again, the improvement came from both better technology and freedom from atmospheric effects. But space telescopes have limitations too. They're incredibly expensive. Hubble cost about $4.7 billion to build and deploy, and maintaining it through servicing missions added billions more. Webb cost about $10 billion. Ground-based telescopes, even large ones, cost hundreds of millions but not billions. Space telescopes can't be easily repaired or upgraded once launched, unless they're in low Earth orbit where astronauts can reach them. And space telescopes are relatively small compared to the largest ground-based instruments. The largest ground-based telescope mirrors are now over 30 feet in diameter, far too large to launch into space with current rockets. This economic and technological reality means that space telescopes and ground-based telescopes serve complementary roles. Space telescopes excel at observations requiring absolute stability, freedom from atmospheric absorption, or wavelengths that don't penetrate Earth's atmosphere. Ground-based telescopes can be much larger, collecting more light for studies of faint objects, and can be continuously upgraded with new instruments. The ideal is to use both, taking advantage of their respective strengths. But there's another approach, one that attempts to bring space-like seeing conditions to ground-based telescopes without actually leaving Earth. This technology, called adaptive optics, emerged in the 1990s and has transformed ground-based astronomy by actively compensating for atmospheric turbulence in real time. It's an elegant solution. Instead of removing the atmosphere, you measure what the atmosphere is doing and correct for it. Adaptive optic systems use deformable mirrors, telescope mirrors that can change shape hundreds of times per second. By measuring how atmospheric turbulence distorts light from a reference star, the system can calculate the mirror shape needed to cancel that distortion. The mirror flexes, creating an equal and opposite distortion that, when combined with atmospheric turbulence, produces a sharp image. The results are remarkable. Large ground-based telescopes with adaptive optics can now achieve angular resolution comparable to, or even better than, Hubble. The European Very Large Telescope in Chile, with adaptive optics, routinely produces images with 0.05 arcsecond resolution, matching Hubble despite looking through Earth's atmosphere. The difference is that this performance requires the adaptive optic system to work correctly, depends on having a bright reference star nearby, and works only in a limited field of view. Hubble's performance is consistent across its entire field of view in any direction, regardless of whether bright stars are available. Still, adaptive optics represents a remarkable achievement, using technology to transform turbulent Earth atmosphere into something approaching the steady clarity of space. It's humanity refusing to accept the limitations nature imposed, finding a way to overcome them through engineering and physics. We'll explore adaptive optics in much greater detail shortly, because the story of how it works, where it came from, and what it can achieve is fascinating in its own right. For now, consider this journey we've taken. From the first human observations of twinkling stars, through understanding that twinkling comes from atmospheric turbulence, to placing telescopes in space where stars shine steadily, to developing technology to stabilize starlight from the ground, each step revealed more about the universe and about the thin shell of air that separates us from it. The question of why stars twinkle turned out to be a gateway to understanding atmospheric physics, optical science, and eventually the nature of light itself. A simple childhood question, why do stars twinkle, led to insights that would reshape how we explore the cosmos. Imagine a telescope mirror that can change its shape 400 times every second, flexing and warping in response to invisible turbulence in the air above it, transforming itself into exactly the right shape to cancel out atmospheric distortion. It sounds like science fiction, a mirror that thinks, that responds, that corrects in real time for problems it can't even see directly. But this technology exists. It's called adaptive optics, and it represents one of the most elegant solutions to a natural problem that humans have ever devised. Instead of accepting that Earth's atmosphere will always blur our view of the cosmos, astronomers decided to fight back. They built systems that could undo atmospheric turbulence faster than it occurs, creating islands of clarity in the turbulent ocean of air. The story of how this became possible involves Cold War military research, brilliant insights about the physics of light, and a technique so counterintuitive that many scientists initially dismissed it as impossible. If this journey through the intersection of science and human ingenuity resonates with you, a like would mean the world, and subscribing ensures you're here for every story we tell. Thank you for exploring alongside me. Let's start with the core problem adaptive optics solves. We've established that atmospheric turbulence distorts starlight, making stars appear to shimmer and causing telescope images to blur. The distortion changes rapidly, typically every few hundredths of a second, and varies across the telescope's field of view. Different parts of the telescope mirror are looking through different turbulent cells at any given moment. Now, here's the key insight that makes adaptive optics possible. These distortions aren't truly random. At any instant, the atmosphere has a specific configuration, a particular arrangement of temperature variations and refractive cells. This configuration is predictable and measurable. If you can measure exactly how the atmosphere is distorting light right now, you can calculate what correction is needed to cancel that distortion. And if you can apply that correction faster than the atmosphere changes, you can create a sharp image despite atmospheric turbulence. The concept was first proposed in 1953 by American astronomer Horace Babcock, who was working at the Mount Wilson Observatory. Babcock realized that if you could measure atmospheric distortion and compensate for it in real time with a deformable mirror, you could dramatically improve telescope image quality. He even sketched out a design for such a system. But 1953 technology couldn't implement his vision. The sensors needed to measure atmospheric distortion didn't exist with sufficient speed or sensitivity. The computers needed to calculate corrections hundreds of times per second were decades away, and the actuators to deform a mirror that precisely and quickly hadn't been invented. Babcock's paper was published, noted by specialists, and then largely forgotten. The idea sat dormant for 25 years, waiting for technology to catch up. The resurrection of adaptive optics came from an unexpected source: military research during the Cold War. In the 1970s, the United States Department of Defense was deeply concerned about Soviet satellites. They wanted to photograph these satellites from the ground to determine their capabilities and configurations. But atmospheric turbulence blurred the images, making detailed reconnaissance impossible. Space-based telescopes weren't yet practical for this purpose, and anyway, The military wanted ground-based systems that could be pointed and repositioned quickly. Defense research agencies revisited Babcock's concept. With substantial funding, much of it classified, they developed the first working adaptive optics systems in the late 1970s and early 1980s. These systems remained highly classified for over a decade. Astronomers knew generally that such research was happening, but details were secret. It wasn't until the early 1990s, after the Cold War ended, that the military declassified enough information for astronomical applications to become feasible. The first major astronomical adaptive optics system came online in 1995 at the 3-meter Shane telescope at Lick Observatory in California. The results were immediately dramatic. Images of binary stars that previously appeared as fuzzy single blobs suddenly resolved into 2 distinct points. Planetary images showed details previously visible only from space probes. The system worked. Adaptive optics could genuinely overcome atmospheric turbulence. So, how does it actually work? Let's break down the components. First, you need a reference source, something bright enough to measure atmospheric distortion clearly. Typically, this is a star near the object you want to observe. The system continuously monitors light from this reference star, measuring exactly how atmospheric turbulence is distorting it. This measurement happens through a device called a wavefront sensor, which analyzes the light's phase, essentially how synchronized different parts of the light wave are with each other. In perfect conditions with no atmosphere, light from a star arrives as a flat wavefront. All parts of the wave are in phase, aligned. Atmospheric turbulence distorts this into a corrugated wavefront, with bumps and valleys corresponding to the optical path, differences through various turbulent cells. The wavefront sensor measures this corrugation in exquisite detail, typically sampling the wavefront at hundreds of points across the telescope aperture. This measurement data feeds into a computer that calculates the mirror shape needed to flatten the wavefront back out. The calculation must account for the telescope's optics, the geometry of the system, and the specific distortion pattern measured. Modern systems perform these calculations in just a few milliseconds, fast enough to keep up with changing atmospheric conditions. The correction is applied by a deformable mirror, a thin, flexible mirror backed by dozens, hundreds, or even thousands of actuators that can push and pull on the mirror surface. When the computer commands push point 47 up by 2 microns and pull point 83 down by 3 microns, the actuators respond in milliseconds, warping the mirror into exactly the shape needed. The deformed mirror introduces distortions that are equal and opposite to the atmospheric distortions. Light that was bent left by turbulence gets bent right by the mirror. Light that was phase delayed by passing through warm air gets phase advanced by reflecting off a depression in the mirror. The 2 distortions cancel, and the light emerges as if it had never passed through atmosphere at all. This correction happens continuously, in a closed loop. The system measures, calculates, corrects, then measures again, adjusting hundreds of times per second to track the changing atmosphere. It's an active, dynamic process. The mirror is never static, always flexing in response to turbulence. The performance improvement is dramatic. Without adaptive optics, even the best ground-based telescopes at the best sites achieve angular resolution of about 0.5 to 1.0 arcsecond, limited by atmospheric seeing. With adaptive optics, the same telescopes routinely achieve 0.05 arcsecond resolution, or better, matching or exceeding space telescopes like Hubble. The atmosphere is effectively removed from the equation, but there's a catch, actually several catches. Adaptive optics isn't a perfect solution. It works beautifully under certain conditions and struggles under others. First, you need a bright reference source. The wavefront sensor needs lots of light to measure atmospheric distortion accurately. This means you need a bright star, typically magnitude 12 or brighter, within about 30 arc seconds of your target object. For much of the sky, no such star exists. Without a reference source, the adaptive optics system can't measure the atmospheric distortion and therefore can't correct it. This limitation was recognized early, and it led to one of the most ingenious solutions in the history of astronomy: artificial stars. If nature doesn't provide a bright star where you need one, create your own. Point a powerful laser into the sky, and it will excite sodium atoms in a layer of Earth's atmosphere about 55 miles up, causing them to glow. This creates an artificial laser guide star that appears from the ground as a magnitude 8 or 9 star, exactly where you point the laser. The first astronomical laser guide star system was deployed at Lick Observatory in 1996. The sight was spectacular. A powerful orange laser beam, visible from miles away, shooting straight up into the night sky, creating an artificial star for the telescope to use as a reference. By 2000, most major observatories with adaptive optics had added laser systems. Laser guide stars aren't perfect. They sample turbulence at 55 miles altitude, but not the turbulence near ground level. Still, they extend adaptive optics to most of the sky, removing the requirement for natural bright stars. Modern systems often use multiple laser guide stars simultaneously, creating a constellation of artificial references that allow measurement of atmospheric turbulence at different angles and altitudes. The second limitation is field of view. Adaptive optics correction is only accurate in a small patch of sky, typically 30 to 60 arc seconds across. Outside this region, the line of sight passes through different atmospheric turbulence, and the correction becomes increasingly inaccurate. This means adaptive optics works wonderfully for small targets, individual stars, planets, small galaxies, but can't correct an entire wide field image. There are advanced techniques to address this. Multi-conjugate adaptive optics uses multiple deformable mirrors conjugated to different atmospheric altitudes, allowing correction over wider fields, up to 2 arc minutes across. But these systems are extremely complex and expensive. Most observatories use single conjugate systems with limited field of view. The third limitation is wavelength. Adaptive optics works better at infrared wavelengths than at visible wavelengths. This is because atmospheric turbulence affects shorter wavelengths more severely. Remember the wavelength dependence we discussed earlier. At infrared wavelengths around 1 to 2 microns, atmospheric effects are reduced, making them easier to correct. Most adaptive optic systems are optimized for near-infrared work. Despite these limitations, the impact of adaptive optics on astronomy has been revolutionary. Let me give you specific examples of discoveries enabled by this technology. In 1998, astronomers using adaptive optics at the Keck Observatory in Hawaii captured the first direct image of a planet orbiting another star, a giant planet circling the brown dwarf, Gliese 229. This was possible only because adaptive optics allowed them to resolve the faint planet next to its much brighter parent star, distinguishing light from the planet against the glare of the star. In 2000, adaptive optics observations of the galactic center, the exact center of our Milky Way galaxy, revealed stars orbiting close to the supermassive black hole Sagittarius A Arst. By tracking the motion of these stars over many years, astronomers calculated the mass of the black hole, about 4 million times the mass of our Sun. This work earned the 2020 Nobel Prize in Physics for Reinhard Genzel and Andrea Ghez, and it was possible only because adaptive optics allowed them to resolve individual stars in the crowded galactic center, tracking their positions with sub-arc second precision year after year. In 2004, Adaptive optics images from the Very Large Telescope revealed surface features on Saturn's moon Titan before the Cassini spacecraft arrived there. The resolution was sufficient to map mountains, plains, and possible lakes, all from Earth through atmosphere, using adaptive optics to achieve clarity that rivaled space probes. The cost-benefit comparison with space telescopes is striking. Building and launching Hubble cost nearly $5 billion. Adaptive optics systems, even sophisticated ones with laser guide stars, cost $10 to $30 million to develop and install on an existing telescope. For certain types of observations, adaptive optics provide space-like image quality at a fraction of the cost. Of course, space telescopes have advantages adaptive optics can't match. Freedom from atmospheric absorption at ultraviolet and infrared wavelengths, stability for long exposures, wide fields of view. But for high-resolution imaging of small targets at near-infrared wavelengths, adaptive optics is often superior and far more affordable. Modern adaptive optics systems have become extraordinarily sophisticated. The Gemini Planet Imager, installed on the Gemini South Telescope in Chile in 2013, uses a deformable mirror with 1,500 actuators, adjusting its shape 1,000 times per second. The system suppresses scattered starlight by a factor of 10 million, allowing detection of Jupiter-like planets orbiting nearby stars. As of 2023, it has discovered over 20 exoplanets through direct imaging. The extremely large telescope, currently under construction in Chile and scheduled for completion in the late 2020s, will have a mirror 39 meters, 128 feet, across. Its adaptive optics system will use 6 laser guide stars and multiple deformable mirrors with over 8,000 actuators total. The expected angular resolution at infrared wavelengths is better than 0.01 arcsecond, 4 times better than Hubble and comparable to the James Webb Space Telescope, from the ground, looking through atmosphere. This is the triumph of adaptive optics, turning a fundamental limitation of nature into a solved problem through technology. The atmosphere will always be turbulent. That's physics, unchangeable. But with fast enough measurements, powerful enough computers, and precise enough actuators, we can undo the distortion in real time, creating windows of clarity through the turbulence. There's something deeply satisfying about this solution. Rather than leaving Earth to escape atmospheric effects, we stay on the ground and simply cancel them out. It's a very human approach. Confronted with a problem, we don't accept it as a permanent limitation. We engineer our way around it. The same technology, incidentally, has medical applications. Ophthalmologists use adaptive optics and retinal imaging systems to correct for optical aberrations in the human eye, allowing visualization of individual photoreceptor cells in living patients. The military uses adaptive optics in laser weapon systems to maintain beam quality through atmospheric turbulence. The technology that emerged from astronomical curiosity and military necessity has found applications far beyond its original purposes. As you lie in bed tonight, if you think about twinkling stars, remember this. Astronomers aren't content to simply observe and explain natural phenomena. They are constantly working to overcome limitations, to see more clearly, to push boundaries. The twinkling that frustrated astronomers for centuries became a challenge they eventually mastered, not by eliminating turbulence, but by measuring and correcting for it faster than it can change. It's a remarkable achievement, born from understanding the physics of atmospheric turbulence deeply enough to actively cancel it. And yet, Earth's atmosphere isn't the only atmosphere in our solar system. Other worlds have their own layers of air, their own turbulence, their own optical effects. Exploring how twinkling would appear from the surface of Mars or Venus or Titan opens up fascinating questions about atmospheric physics under different conditions, and about what the night sky looks like from worlds beyond Earth. Imagine standing on the rust-colored surface of Mars, looking up at the night sky. Earth would be visible, a pale blue dot, bright enough to cast shadows. But would it twinkle? Would the stars above you shimmer and dance the way they do from Earth's surface? The answer depends on Mars's atmosphere, thinner than Earth's by a factor of 100, composed of different gases, producing different turbulence patterns. Every world with an atmosphere creates its own version of stellar scintillation, its own characteristic way of bending and scattering starlight. And here's what's fascinating. By studying how atmospheres affect starlight, whether on Mars, Venus, or planets orbiting distant stars, we've turned the problem of twinkling into a scientific tool. The phenomenon that frustrated astronomers for centuries now helps us discover and characterize worlds we could never visit, revealing the composition, structure, and weather patterns of alien atmospheres across the cosmos. If this cosmic perspective expands your sense of wonder, I'd be grateful for your like and subscription. It's what allows these explorations to continue. Thank you for being here. Let's start close to home, with Mars. NASA's Viking landers, which touched down on Mars in 1976, didn't include astronomical observations in their mission plans. They were focused on soil chemistry and searching for signs of life. But subsequent missions, particularly the Mars exploration rovers Spirit and Opportunity, which arrived in 2004, did capture images of the night sky. The Curiosity rover, landing in 2012, and Perseverance, arriving in 2021, have sophisticated cameras capable of nighttime observations. What these rovers revealed is that stars do twinkle from Mars, but differently than from Earth. Mars's atmosphere is about 1% the density of Earth's, mostly carbon dioxide, with average surface pressure of just 6 millibars compared to Earth's 1,013 millibars. This thin atmosphere produces weaker turbulence and less dramatic scintillation. Stars twinkle on Mars, but gently, subtly, far less than the vigorous shimmering visible from Earth. But Mars has something Earth doesn't: enormous dust storms that can engulf the entire planet. During these storms, the atmosphere becomes thick with suspended dust particles, and the optical effects become extreme. Rovers have photographed the sun during dust storms appearing as a dim, diffuse glow, all direct light scattered by dust. Stars become nearly invisible, not because of twinkling, but because the dust simply blocks and scatters their light before it reaches the surface. Between major dust storms, Mars's atmosphere is relatively calm and clear. The thermal turbulence is limited because Mars receives less solar heating than Earth. And the thin atmosphere can't sustain the vigorous convection cells that create turbulence on Earth. Calculations by planetary scientists suggest that a telescope on Mars would experience seeing conditions of perhaps 0.2 to 0.3 arcseconds, better than most Earth-based sites, though not as good as the best Earth mountaintop observatories. Mars could be an excellent location for optical astronomy once we establish a permanent presence there. Now let's travel to Venus, Earth's so-called sister planet. Similar in size, but radically different in almost every other way. Venus has an atmosphere 92 times denser than Earth's, composed of 96% carbon dioxide, with clouds of sulfuric acid extending from 30 to 40 miles above the surface. The surface pressure is 92 bar, equivalent to being 3,000 feet underwater in Earth's oceans. No spacecraft has ever captured images of stars from Venus's surface. The Soviet Venera landers that reached the surface in the 1970s and 1980s operated for only a few hours before being destroyed by the extreme heat and pressure. and their missions occurred during Venusian daylight. But we can model what stellar observation from Venus's surface would be like, and the answer is dramatic. You couldn't see stars at all. Venus's thick cloud layers completely obscure the surface. Visible light doesn't penetrate. The sky from Venus's surface during the Venusian day glows a dim orange, diffuse sunlight scattered through clouds. At night, it would be essentially black. No stars, no moon. Venus has no moon. No celestial objects visible at all. The atmosphere is so dense and the clouds so thick that Venus's surface is isolated from the cosmos, perpetually shrouded. But if you could somehow float at the top of Venus's cloud layer, about 40 miles up, where the atmosphere is thinner and clearer, stellar observations would show extreme scintillation. The temperature variations and turbulence in Venus's atmosphere are severe. High-altitude winds reach 220 miles per hour, circling the planet every 4 days in what's called superrotation. This creates powerful turbulence and sharp refractive gradients. Stars visible from Venus's upper atmosphere would twinkle wildly, perhaps flashing on and off completely, showing color changes far more dramatic than anything visible from Earth. Now, let's venture to the outer solar system, to Saturn's largest moon, Titan. Titan is one of the most Earth-like worlds in the solar system. Not in terms of temperature, it's a frigid minus 290 degrees Fahrenheit, but in having a thick nitrogen atmosphere and a complex weather system with rain, clouds, lakes, and rivers. Titan's atmosphere is about 50% denser than Earth's at the surface, composed mainly of nitrogen with methane and organic haze particles. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, released the Huygens probe, which landed on Titan's surface in January 2005. Huygens captured images during descent and from the surface. Hazy, orange-tinted landscapes under a dim, diffuse sky. But Huygens landed during Titan's day and operated for only 90 minutes, so it never observed stars. However, we can model stellar scintillation from Titan based on atmospheric measurements. Titan's atmosphere is dense and layered, with complex haze extending from the surface to over 300 miles altitude. The haze scatters light strongly, which would make stars appear dimmer than from Earth or Mars. But the atmospheric density and turbulence would also cause noticeable twinkling, perhaps more vigorous than Mars, but less than Earth, with the added complication that the haze would create additional scattering effects, possibly making stars appear surrounded by diffuse halos. One fascinating aspect of Titan is that methane plays the role water plays on Earth. It evaporates, forms clouds, rains out, and cycles through the environment. This creates weather patterns and atmospheric turbulence driven by methane convection. An astronaut standing on Titan during a methane rainstorm would see a dark, hazy sky with stars obscured by clouds. On clear nights, stars would twinkle through the haze, appearing orange-tinted from the scattered light. Let's consider the gas giants, Jupiter, Saturn, Uranus, Neptune. These worlds have no solid surfaces. They're mostly atmosphere all the way down until pressure and temperature become so extreme that hydrogen transitions to liquid metallic states. Could you even see stars from inside a gas giant atmosphere? The answer depends on depth. In the upper atmospheres, above the cloud layers, stars would be visible. But these regions are turbulent beyond anything on Earth. Wind speeds on Jupiter reach 400 miles per hour. Temperature gradients are extreme. The refractive effects would be spectacular. Stars would scintillate wildly, appearing to jump around, flash on and off, change colors dramatically. The turbulence is so strong that adaptive optic systems designed for Earth wouldn't come close to correcting it. Deeper in the atmosphere, where clouds form and thicken, stars would become increasingly obscured, Eventually, at depths where the atmosphere is effectively opaque to visible light, stars would be invisible. You'd be surrounded by glowing atmosphere, lit from within by the planet's internal heat, with no view of the cosmos beyond. Now, let's make the leap to exoplanets, planets orbiting other stars. We can't visit these worlds, at least not with current technology, but we can study how their atmospheres affect starlight. And this has become a powerful tool for characterizing these distant worlds. When an exoplanet passes in front of its star, an event called a transit, some of the star's light passes through the planet's atmosphere on its way to us. The atmosphere absorbs certain wavelengths based on its composition. By carefully measuring which wavelengths are absorbed, astronomers can determine what gases are present in the exoplanet's atmosphere. This is called transmission spectroscopy. The first atmospheric detection of an exoplanet came in 2001, when scientists using the Hubble Space Telescope observed sodium in the atmosphere of HD 269458b, a gas giant orbiting a sun-like star 150 light-years away. Since then, astronomers have detected water vapor, methane, carbon dioxide, and even clouds and haze in the atmospheres of dozens of exoplanets. Here's where stellar scintillation becomes relevant. The technique depends on measuring tiny variations in starlight, often less than 1%. Earth's atmospheric scintillation adds noise to these measurements. Observations must be made from space, or with extremely careful atmospheric correction from the ground, to achieve the necessary precision. The twinkling that poets celebrate becomes noise that scientists must overcome. But there's a beautiful twist. Atmospheric scintillation on the exoplanet itself can tell us about that planet's atmosphere. Some hot Jupiter exoplanets, gas giants orbiting very close to their stars, have been observed to show variations in brightness as they orbit. Part of this variation comes from their atmospheres being heated and stretched by tidal forces, creating turbulence and temperature gradients. The planets themselves exhibit a form of scintillation as their turbulent atmospheres bend and scatter light from the star behind them. In 2019, astronomers detected something remarkable in observations of WASP 76b, a hot Jupiter where temperatures reach 4,400 degrees Fahrenheit. The planet's atmosphere is so hot that iron vaporizes, and atmospheric circulation patterns create an extreme day-night temperature difference. On the cooler night side, iron condenses and literally rains from the sky. The atmospheric turbulence from this process creates detectable variations in the planet's spectrum. Essentially, the atmosphere is twinkling, and we can see it from 640 light-years away. This opens a profound realization. Stellar scintillation is a universal phenomenon. Any star viewed through any turbulent atmosphere will twinkle. The details, the intensity, the time scale, the wavelength dependence, depend on the specific properties of that atmosphere. But the basic physics is the same throughout the universe. We can even use stellar scintillation to study atmospheres we can't directly observe. When a star passes behind Titan as seen from Earth, an event called an occultation, the star's light passes through Titan's atmosphere before reaching us. By measuring how the starlight changes during the occultation, astronomers can map temperature and density variations in Titan's atmosphere at different altitudes. The twinkling of the star as it's occulted tells us about atmospheric structure. This technique has been used to study not just Titan, but many other solar system bodies with atmospheres. Pluto during stellar occultations in the 2000s and 2010s, Neptune's moon Triton, even Jupiter's Galilean moons, Io and Europa, which have extremely thin atmospheres of sulfur dioxide and oxygen, respectively. In each case, the way starlight scintillates as it passes through these tenuous atmospheres reveals their structure and composition. There's something poetic about this application. For centuries, stellar twinkling was seen as a nuisance, an atmospheric effect that degraded observations. Now, we recognize it as information. The way an atmosphere distorts starlight tells us about that atmosphere's temperature, pressure, composition, turbulence, and structure. Twinkling has become a tool, not a problem. Let's venture into more speculative territory. Imagine standing on a world orbiting a red dwarf star, the most common type of star in our galaxy. Red dwarfs emit most of their light at infrared wavelengths, with much less visible light than our sun. If such a planet had an Earth-like atmosphere, how would stars appear? The reduced visible light would make everything dimmer, but the infrared emission would be strong. To human eyes adapted to Earth's sun, the sky would appear dim and reddish. Stars would still twinkle, but the dominant wavelengths causing scintillation would be in the red and infrared, not the blue and green that dominate on Earth. The chromatic scintillation, the color changes, would be different, with stars perhaps appearing to shift between dark red and brighter orange rather than between blue and red. Or imagine a planet orbiting a binary star system, two stars circling each other. Such systems are common in our galaxy. A planet in a stable orbit around a binary would see two suns in the sky. At night, with both stars below the horizon, other stars would be visible and would twinkle normally. But during twilight, with one or both stars near the horizon, the sky would be bright enough that most stars would be invisible, visible only during the hours when both suns were well below the horizon. What about planets with very different atmospheric compositions? A world with a helium-rich atmosphere, for instance, would have different refractive properties than Earth's nitrogen-oxygen atmosphere. Helium has a lower refractive index than nitrogen, so atmospheric turbulence would cause less bending of light. Stars would twinkle, but less vigorously. An astronaut on such a world might notice that stars appear more stable than they do from Earth. Conversely, a planet with a very thick atmosphere of heavy gases, perhaps carbon dioxide and argon, like Venus, but cooler and clearer, would show more vigorous twinkling. The higher density and refractive index would amplify atmospheric effects. Stars might appear to flash and jump around dramatically, making astronomical observations from the surface challenging. There's a limit to this speculation without real data, but the principles are universal. The physics of refraction, of turbulence, of scintillation applies throughout the universe. Anywhere there's atmosphere and starlight, there will be twinkling. The details vary, but the phenomenon is cosmic in scope. This universality connects us to the rest of the cosmos in an unexpected way. When we look up and see twinkling stars, we're experiencing a phenomenon that occurs on countless worlds throughout the galaxy. On some worlds, the twinkling is gentle and subtle. On others, it's wild and dramatic. On airless worlds, there's no twinkling at all. Each world's atmosphere creates its own characteristic signature, its own way of interacting with starlight. And yet, throughout all this diversity, the fundamental question remains the same. What is the true nature of the light reaching us from the stars? Is the twinkling real, or is it illusion? Are stars truly dancing, or is it our atmosphere playing tricks? We've answered this question scientifically. The stars are steady. The twinkling is atmospheric. But there's a deeper truth here, one that goes beyond physics and touches something more fundamental about perception, beauty, and our relationship with the cosmos. So, we've traveled far, from ancient Babylonian ziggurats, where priests first noticed the difference between twinkling stars and steady planets, through medieval observatories where sailors cursed the dancing lights that made navigation treacherous, into the physics laboratories where scientists unraveled the mathematics of refraction and turbulence. up to mountaintop observatories where laser beams pierce the sky creating artificial stars, and finally outward to other worlds where different atmospheres create their own versions of this cosmic shimmer. We have asked a simple question: why do stars twinkle? And found answers that span atmospheric physics, optical science, astronomy, and even philosophy. But now, as we near the end of this journey, I want to ask a different question. What do we lose when we eliminate twinkling? What is sacrificed when we achieve perfect clarity? Consider this. Nearly every culture in human history has poetry about twinkling stars. Twinkle, twinkle, little star, which you probably learned as a child, dates to 1806, written by English poet Jane Taylor. The poem expresses wonder at the diamond-like quality of stars, up above the world so high, like a diamond in the sky. That diamond quality, the sparkle, the flash, the sense of life and vitality, comes entirely from atmospheric scintillation. Taylor wasn't describing stars as they actually are. She was describing stars as they appear through Earth's turbulent atmosphere. John Keats, the Romantic poet, wrote in 1819 of the trembling stars. Samuel Taylor Coleridge described the twinkling stars in The Rime of the Ancient Mariner. Walt Whitman, in When I Heard the Learned Astronomer, contrasts the dry calculations of astronomy with the experience of going outside and looked up in perfect silence at the stars, stars that, from Earth's surface, would be twinkling. The twinkling isn't separate from the aesthetic experience. It's central to it. Vincent van Gogh's The Starry Night, painted in 1889, shows stars as dynamic, swirling presences in the sky, each surrounded by halos of light. Van Gogh wasn't painting astronomical accuracy. He was painting the experience of seeing stars from Earth, including the optical effects of atmosphere. The painting wouldn't work if the stars were rendered as perfect, steady points. The energy, the motion, the sense of cosmic vitality comes precisely from the distortions that Earth's atmosphere introduces. This matters because it reveals something profound. The imperfection creates beauty. The distortion creates meaning. Stars as they actually are, steady, unwavering points of light in the vacuum of space, are in some sense less compelling, less emotionally resonant than stars as they appear through our atmosphere. Remember the astronaut testimonies we discussed earlier? Neil Armstrong, Buzz Aldrin, Eugene Cernan, all reported that stars from the moon looked cold, hard, too perfect. They found the absence of twinkling unsettling, not reassuring. The steadiness that astronomers strive for in their observations was, for these explorers, a source of alienation. The universe without atmospheric distortion felt less welcoming, less alive. There's a parallel here with other forms of imperfection. Music without any variation in tempo or dynamics. Perfectly mechanical music sounds robotic, lifeless. Photographs that are too sharp, too perfectly processed, can look artificial, less engaging than images with slight grain or blur. Japanese aesthetic philosophy has a concept called wabi-sabi, finding beauty in imperfection, in impermanence, in incompleteness. The twinkling of stars, viewed through this lens, isn't a flaw to be corrected. It's a reminder of our perspective, our position at the bottom of an ocean of air, our connection to this particular planet. Scientific understanding doesn't diminish this beauty, it deepens it. Now, when you see stars twinkling, you can perceive the invisible atmosphere, the currents and eddies of air, the temperature variations and turbulent cells that we spent so much time exploring. The shimmer becomes visible evidence of atmospheric dynamics, a window into processes usually hidden from sight. You can watch Sirius near the horizon, flashing blue and red and white, and recognize chromatic dispersion. the same physics that creates rainbows, now playing out at the threshold of perception, separating starlight into its component colors and recombining them dozens of times per second. The beauty isn't separate from the physics. The beauty emerges from the physics. Let me share one more story, a personal account from astronomer James Kaler, who spent 40 years studying stellar spectra at the University of Illinois. In his memoir, published in 2006, Kaler describes his first night at a professional observatory. He was 23, a graduate student using a large telescope for the first time. The telescope was pointed at Arcturus, a bright orange giant star. Kaler watched through the eyepiece as the seeing conditions varied. During moments of calm air, Arcturus appeared as a tiny, sharp point, beautiful in its precision, but almost abstract. Then the atmosphere would stir, and Arcturus would begin to dance, to shimmer, to pulse with light. Kaler found himself preferring the twinkling. The star seemed more real, he wrote, more present when it was imperfect. This tension between scientific ideal and human experience runs through the entire history of astronomy. Scientists want perfect, undistorted observations. They build space telescopes and adaptive optic systems to eliminate atmospheric effects. They seek truth, which means seeing things as they are, not as they appear. And yet, the appearance, the twinkling, the shimmer, the dance of light through air, is part of our relationship with the cosmos. It's how humanity has always seen stars for our entire existence as a species. There's no contradiction here. We can appreciate both perspectives. We can value the scientific clarity that comes from removing atmospheric distortion, while also treasuring the aesthetic experience of twinkling stars visible from Earth's surface. These aren't opposing views. They're complementary ways of engaging with the universe. The physicist Richard Feynman once gave a famous description of this duality. A poet friend told him that Feynman's scientific understanding of flowers must diminish their beauty, reducing them to molecular structures and evolutionary adaptations. Feynman disagreed. The beauty that the poet sees, Feynman said, is available to him too. But on top of that beauty, he can also perceive the mechanisms that create it, the chemistry of pigments, the co-evolution with pollinators, the genetic information encoding flower structure. The scientific understanding doesn't replace the aesthetic experience. It adds layers. The same applies to stellar twinkling. The shimmer that inspired poets and painters for millennia is still there, still beautiful, still capable of evoking wonder. But now, we can also perceive the atmospheric physics, the refractive dynamics, the turbulence patterns that create that shimmer. We understand that the stars themselves are steady, but that understanding doesn't eliminate the beauty of seeing them dance through Earth's atmosphere. So, what's the lesson here? Perhaps it's this: nature reveals itself on multiple levels. There's the immediate sensory experience, stars twinkling in the night sky, a phenomenon so ubiquitous that humans barely questioned it for thousands of years. There's the mechanistic explanation, atmospheric turbulence causing refractive variations in starlight. There's the technological response, space telescopes and adaptive optics to achieve clarity. And there's the reflective understanding, recognizing that the imperfection of twinkling is itself a kind of gift, connecting us to our atmosphere and our planet in a way that perfectly steady starlight never could. When you go outside tonight, or any clear night, and look up at the stars, you're seeing through 60 miles of churning air. Every photon that reaches your eye has navigated thousands of turbulent cells, each bending the light slightly, creating that characteristic shimmer. The star itself, perhaps a sun like ours, perhaps a giant hundreds of times larger, perhaps a dying ember of white dwarf slowly cooling, shines steadily across light years of space. But in its final moments of travel, passing through Earth's atmosphere to reach your eye, its light is transformed. That transformation is the story we've told today. It's a story that begins with human curiosity, why do stars twinkle, and unfolds into atmospheric physics, optical science, technological innovation, and ultimately, a deeper appreciation for our place in the cosmos. We live at the bottom of an ocean of air, and that air shapes how we see the universe beyond. Understanding this doesn't diminish the experience, it enriches it. Think about what we've covered, the ancient observations that first distinguished twinkling stars from steady planets, leading to the recognition that planets were fundamentally different objects. The atmospheric structure that creates turbulence, layers of air at different temperatures, circulating in the complex patterns, creating refractive cells that bend starlight. The physics of refraction itself, described mathematically by Snell's law, predicting exactly how light bends when moving between media of different densities. The three components of scintillation, positional wandering, intensity fluctuation, and chromatic variation, each telling us something different about atmospheric turbulence. The angular size solution that explains why planets don't twinkle, spatial averaging across an extended disk, canceling out atmospheric variations. The view from space, where stars shine with unwavering steadiness, revealing both the clarity we gain and the vitality we lose when we eliminate atmospheric effects. The brilliant solution of adaptive optics, measuring and correcting for atmospheric distortion faster than it changes, bringing space-like clarity to ground-based observations. And finally, the recognition that stellar scintillation is a universal phenomenon occurring on any world with an atmosphere, connecting us to countless other worlds throughout the cosmos. Each piece of this story reveals something about how science works. We observe a phenomenon, stars twinkling. We develop hypotheses, Aristotle's weak vision theory, Alhazen's atmospheric refraction, eventually the modern understanding of turbulence. We test these hypotheses through observation and experiment. We refine our understanding. We develop technology to overcome limitations. And ultimately, we arrive at a comprehensive explanation that not only answers the original question, but opens up new questions and new applications. The story doesn't end here. Atmospheric science continues to advance. New adaptive optics systems push the boundaries of what's possible from ground-based telescopes. Exoplanet characterization through atmospheric studies reveals the nature of worlds light years away. And perhaps most importantly, future generations will continue to look up at twinkling stars and wonder, just as humans have for millennia. Have you ever really paid attention to stellar twinkling? Next time you're under a clear sky, take a few minutes to watch a bright star carefully. Notice how the brightness varies, not smoothly, but in rapid, irregular pulses. If it's near the horizon, watch for color changes, flashes of blue, red, white. Compare stars at different elevations. Notice how stars low on the horizon twinkle vigorously, while stars overhead shimmer more gently. Look at planets if any are visible, Venus, Jupiter, Mars, and observe their steady, unwavering light, so different from the dancing stars around them. These observations, which you can make with no equipment beyond your own eyes, are the same observations that puzzled and intrigued astronomers for thousands of years. You're engaging with the same questions that motivated Babylonian priests, Greek philosophers, Arabian scientists, Renaissance navigators, and modern astrophysicists. The phenomenon hasn't changed, only our understanding of it has evolved. And that evolution continues. Every generation discovers something new about stellar scintillation. The development of extremely large telescopes, mirrors 30 to 40 meters across, will require adaptive optics systems far more sophisticated than anything that exists today, measuring and correcting atmospheric distortion at unprecedented scales. The characterization of exoplanet atmospheres through transit spectroscopy will become more precise, revealing the composition and structure of alien air. The search for biosignature gases, molecules that might indicate life on other worlds, depends on measuring atmospheric absorption with exquisite precision, distinguishing genuine signals from noise caused by Earth's twinkling atmosphere and the exoplanet's own atmospheric effects. The simple question, why do stars twinkle, has led us on a journey through physics, astronomy, technology, and philosophy. We've discovered that the answer involves atmospheric turbulence, refractive optics, wavelength-dependent dispersion, and the three-dimensional structure of Earth's atmosphere. We've learned that the phenomenon isn't unique to Earth. Every world with an atmosphere creates its own version of stellar scintillation. We've seen how scientists have developed technologies to overcome atmospheric limitations, from space telescopes to adaptive optics. And we've reflected on the aesthetic and emotional dimensions of twinkling, recognizing that the imperfection creates a kind of beauty that perfect clarity might lack. As you drift towards sleep tonight, perhaps thinking about the stars above, whether you can see them or not, they're there, shining through the atmosphere, their light dancing its final dance before reaching Earth's surface. Remember this, you're connected to every human who ever looked up and wondered. The stars you see are the same stars that ancient astronomers studied, that navigators used to cross oceans, that poets celebrated in verse. The twinkling you observe is the same phenomenon that puzzled Aristotle, intrigued Alhazen, challenged Galileo, and ultimately inspired the development of adaptive optics and space telescopes. Science has given us the answer to why stars twinkle, but more than that, it's shown us how to ask better questions, how to observe more carefully, how to think more deeply about the universe and our place in it. The story of stellar scintillation is, at its heart, a story about human curiosity, about noticing the world around us, wondering why it is the way it is, and refusing to accept that's just how things are as a final answer. So, here's my invitation to you. The next clear night, go outside, look up, watch the stars twinkle. Let yourself experience the beauty of it, the diamond-like sparkle, the gentle shimmer, the sense of vitality and motion in the heavens. And then, layer onto that aesthetic experience the knowledge you've gained today. See the invisible atmosphere, the turbulent cells of air, the temperature variations creating refractive gradients. Recognize that you're watching light that has traveled for years or centuries across space, only to have its path bent and scattered in the final seconds of its journey by Earth's restless air. Both perspectives, the aesthetic and the scientific, are true. Both are valuable. Both enrich your experience of the cosmos. The stars twinkle because of atmospheric turbulence, and that turbulence is beautiful. The imperfection creates wonder. The distortion reveals truth. The shimmer connects us to our planet and to the universe beyond. Thank you for joining me on this exploration. Thank you for your curiosity, your patience, your willingness to dive deep into a question that seems simple but reveals layer after layer of complexity and beauty. The universe is full of such questions, phenomena we take for granted until we stop to really look at them, to ask why they happen, to trace the chains of cause and effect that create the world we experience. This is just one story among countless others waiting to be told. The cosmos is vast, filled with mysteries both ancient and newly discovered. Each mystery, when explored with care and curiosity, reveals something profound about the nature of reality and our ability to understand it. So rest well tonight, knowing that above you, stars are shining through turbulent air, their light dancing in that eternal, beautiful shimmer. And when you're ready for the next journey, the next deep dive into cosmic wonder, I'll be here, ready to explore alongside you. Until then, look up, wonder, and remember, the stars don't actually twinkle. But isn't it beautiful that they appear to? Sweet dreams, fellow traveler, and clear skies.